haven't been this excited since Bitcoin hit 20 grand. So super excited to have you here. Has anyone been to all four of the DataEngConfs in New York? Yeah, awesome. So many hands went up. You guys couldn't see. So we have a really great show, really great program lined up. I want to introduce myself. I'm Pete Soderling. I'm the founder of DataEngConf and the company that runs it called Hacker Labs. If you want to hear stories about sad entrepreneur trying to build amazing things for software engineers, you can chat with me in the hallway and I'll tell you all about how that goes for those of you startuppers out here. But we're super excited to have you. This is our fourth event, as I mentioned. We're back at Columbia for the second year in a row. And we have lots of great things lined up, so welcome. I just want to make a few announcements before we get to the meat of the keynote. But we have a code of conduct. I wanted to mention that straight off. You can find it online on our website. I think for the most part, behavior and sort of acceptable norms is something that we are all sensitive to. I hope that's the case. If not, definitely make sure you check out what we consider to be acceptable conduct, and you can do so here. So DataEngConf is a 2-day community-powered event, and we're proud to tell the technical stories of data platforms, data science, analytics, and other forms of interesting, novel, cutting-edge data goodness. We're a deeply technical conference. There's some other data conferences out there that aren't. We're run by and for data engineers and data scientists. We have an awesome group of folks besides me who help screen, pick, and invite speakers and talks. So all of our talks are vetted by the community, and we make sure that they're sort of oriented for maximum technical content. You'll also find that we have an interesting concept that's been super successful since we launched in the speaker office hours. So after each session, on each track, we'll have a few minutes for Q&A, but then we have a more extended period for speaker office hours where you can follow the speaker into the side room and continue a conversation with them, asking them questions. It's a great time for one-on-one or one-on-group conversations and to understand what the projects are working on. So make sure that you avail yourself to the speaker office hours. They're one of the best parts of the conference and consistently get high ratings from speakers and attendees alike. Also, don't forget, we have a data community party tonight, which is a short walk from the venue. It's a few minutes away. And we'll have more information about that later. And, one other thing, one of the interesting, fun pieces of the schedule that we put together each year is something special for startup founders. So if you're a technical founder at a startup, or if you want to start a company, we'll be having a founders panel today. That's at 4 p.m. It's in the AI products track room. And I'll give you a little bit more info on where to find the schedule later on. So what else makes DataEngConf different? There's lots of data conferences out there, and there's a couple other things that we hold to as differentiators and brand principles that we keep coming back to as a team over and over and over again. And one of the big words that we use a lot as we're planning our next events is community. There's many conferences out there that sort of swoop in every year, try and get you to come, try and sell you tickets, and perhaps don't have that much anchor or place in the community. This is an area where we sort of firmly believe that helping the local data community is important, and we see DataEngConf as only the representation of us stitching together all the other existing parts of the data community. We just happen to be here every year, and we get to sort of pull everyone in the same room. So you'll see this through the meetups that we run. In each city that we've launched a conference, we run a meetup that runs year-long. We run 3 events. They're community organized, led by volunteers. So if you have experience or meetups in New York City, San Francisco, or Barcelona, you can do that. And you can find them on meetup.com, the DataEng meetup series. Also, I'm excited to announce that we went international this summer, and in September we launched our first DataEngConf in Barcelona. We had hundreds of attendees from 20 different countries between San Francisco and Japan. this side of the land in it, not the ocean side. So we were super excited that we had such an outpouring of interest from the international community. So know that you're part of not just a local event, but that you're part of an international event, and we're continuing to expand DataEngConf worldwide. These are the meetups that we run, as I mentioned. They're growing all the time, and we're always looking for interesting community organizers who are connected to the data eng and data science space. So if you're here from another city and want to get in touch with us about what it takes to start a data eng meetup in your city with our support, we have a broad global network that we can plug you into, and we can help you find speakers, we can give you tips on running the meetups, and we're happy to help market and promote those as well. So we're continuing to expand this footprint, and we rely on the community for your support of the meetup series. We also like to think of ourselves as a no bullshit data event. So if you detect anything that doesn't meet your standards in any way, please email us. community@hackalabs.co is how you can reach us, and we're always looking for feedback. We want this to be a super inspiring, meaningful, technical event for the community. So if you have anything that you want to sort of mention to us or feedback that you want to give, we're always happy to field that and direct that to the right folks so that we can improve in the future. So I want to introduce two new tracks that we have this year. We're always playing with the content areas of the conference. We have our core data engineering track, which will be in this room. We have our data science and analytics track, which is out these doors and up the elevator to floor number 2, and it's actually this room right behind you, this sort of mezzanine level that's closed off. That's the theater where the data science and analytics track will be held. And then the two new tracks that we're featuring this year that are somewhat experimental, but have grown out of some discussions and things that we've done in the past, are the AI products track is one. The AI products track will run today, and the Hero Engineering track will run in the same room tomorrow, so this is sort of a split track. And the idea here is to feature different types of content that are interesting for different folks. So the AI products track is more about applied, weaponized versions of data pipelines, analytics, machine learning models inside product form. So again, if you're a startup and if you're interested in sort of what the newest products are out there that are actually taking a lot of the data science models and putting them into production in interesting, novel ways, the AI products track could have some interesting stuff for you. And then that's complemented by the Hero Engineering track. What do we mean by Hero Engineering? Maybe it's the opposite of Cowboy Engineering. Hero Engineering is what we mean when we see small teams who do a lot with few resources. So again, typically, perhaps lots of startups can potentially fit into this track, but someone who has a full stack appreciation of what it means to build a data product. I remember the very first talk at DataEngConf 4 years ago was by the Spotify machine learning team, and they told us a story about how they had built end-to-end Discover Weekly. And this was before Discover Weekly was really a thing. They were just launching it at the time. And it was a great example of an engineer who had sort of a product sense, but was able to design the model and design some of the algorithms to power that whole product experience and that whole feature along the way. So these are the types of stories that you might hear on the Hero Engineering track, stories of teams that do a lot with few resources. Obviously, we're on social media, so we like it when you guys are as well. Share your comments, share your thoughts, share interesting tidbits with your network. And if you want to stay connected with us there, that's the first place where you can get the speaker slides that we have available for download. So make sure you follow the hashtag DataEngConf. These are our awesome sponsors. We have so many of them this year. They're all here. They're in this gallery behind you and out here as well by the food area, scientists and their teams. Some of them have really cool, interesting data tools that they can demo for you. But all of them have engineers here, and they're all interested in chatting with you. So we don't have dedicated sponsor time where we tell you to go and talk to them, because that would be stupid. Instead, we intertable, so we encourage you to go out and chat with them and make time for that. So I also want to, I thought we had one more slide here, no worries. So I'll give you some updates on the schedule later, but before I do that, I want to introduce Baron Schwartz. Baron is our keynote at Cortex, founder and CTO, and before that, he was Chief Performance Architect at Percona. So suffice it to say that for folks who understand the internal workings of database performance, as office hours following the talk, but without further ado, please welcome me in, join me in welcoming Baron.
A super interesting guy, and I love it. Let me get this slide to switch over here. Developing software and then discovering that I loved databases more, I started writing on my blog about pretty much everything that I was for 4 or 5 years, something like that, through the fast growth period of MySQL and Web 2.0. And so I got to consult alongside a bunch of code of the database rather than the code that people were running in the database. And that led me to understand a performance-based mindset. And after a while, it's Percona monitoring plugins now. So this is all open source software that I wrote, some of which is still widely used today. But after a while, I realized this could be turned into a product, or these ideas could be turned. You know, if you have large-scale MySQL, Postgres, MongoDB, Redis, measure what it's doing, then we are a great way to measure that at any scale with essentially zero performance overhead, which is great. These slides are going to be online. I've got an introduction slide here. I'm going to skip past because that's for people who are viewing this and how to sort of approach it in a productive way. We'll start with a typical way that a lot of people do this, which is through the science of computer performance as the utilization, because it's where a lot of the existing literature is. And I'll kind of find what scalability means from a similar kind of mathematical perspective. There's no need for any mathematical knowledge here. What I really want to do is just build intuition through all of these things. After that, we'll extend Amdahl's law into the universal scalability law, which is a relatively recent articulation of the math of how systems scale. And then we'll see how to apply that in the real world using one of our servers that I just grabbed some data from last night as kind of a test data. And then we'll see, give you some foundation for maybe going deeper on queuing theory if you want to. But queuing theory is this, and Gene Amdahl was, sorry, I'm completely hyperlink, was trying to answer the question, how many lines do we need open? We don't have to wait too long in line to check out for groceries, things like that. It's all kinds of waiting analysis to be processed, and when they arrive irregularly or when there are too many of them to fit into the available time for processing, If you don't have a queue, then if a job arrives at a system and there's another job in process, then it's unavailable and the job has to fail. And this could be a request response in a web server, or a query to a database or server, or arriving at the check. When you have a queue in front of it, it's one more thing, more ability for the system to have a job ready to process when it is ready. And his talk at Lisa is on YouTube, and all that stuff is in the vertical side. So it's kind of a visualization that a job arrives and it's with a 45-degree slope. And the server is processing it during that time. Well, we get a red parallelogram. And here I'm going to introduce just a little bit of the queuing notation. So R is the residence time, response time. You can also do the job to actually run. That's the time that it takes for the cashier to actually do your groceries, for example. And if we have multiples of these things, you can see how the queues kind of pile up. Maybe requests even stack relate the vertical and horizontal dimensions here and derive this equation. Now this is an equation that can be derived. Wait time in the queue, it's not the total response time. And you get this, this formula, which is related in terms of how long it takes a job to be done and how fast they. And then I draw a picture of what the curve of that looks like. I translated it into the utilization domain, which is typically how queuing, the aspect ratio is highly skewed. To flatten it out, it's actually much steeper than that. But generally what happens is as utilization increases and gets close to 1, and utilization cannot go, they very non-linearly get much less responsive, and customers, or the wait time equation, is that you can look at it and kind of intuit some things from it very easily. So just as a thought experiment, so the queue wait is very sensitive to the service time. Those things are related to each other very, very closely. Therefore, how much they're going to overlap, because overlapping is what contributes to that explosion. And they start kind of pushing back at you, and everybody gets a miserable experience who's a customer of this system. But the hard part is how you actually translate this into price. It actually turns out to be measuring the service time and inter-arrival times and understanding the statistical distribution of those things. Literally any system. Queuing starts before the system starts getting very busy at all. Even if it's a small amount of queuing, it is there. And it escalates really suddenly, not escalated fast. And it's now, I said wrap it out of the hat, bait and switch. I'm going to switch into that next, and then I'll introduce the other cause of nonlinear scalability a little bit later. All right, so let's switch into a relationship called Amdahl's law. That's kind of the gist of it, is how much speed up you get from parallelability is a function of concurrency. Remember those triangles stacked on top of each other? When there's one triangle, there's concurrency of one. When you've got one stacked on top, waves both radiate in performance theory. One way or another, concurrency is at the root of it. I talked about a mathematical definition of scalability that follows from concurrency. Concurrency is also the canonical definition of system load. So we can think of scalability in terms of system load as well. 1/3 of the original response time, right? And completions over time, right? So we're seeing a function here that throughput is a function of divide this into 3 equal parts, then we can do 3 times as many of them, right? So with concurrency of 3, we will get 3 times the throughput. So now I'm starting to relate concurrency. Relationship is really important. And our ideal scalability is linear. There's lots of marketing talk about linear scalability. When you do the math on it, just take some of the measurements, so it's really easy to figure out whether you've got truly linear scalability or not. All right, so this is linear scalability, and this is our ideal. If 1 unit of concurrency produces 1 unit of throughput, like that, if you actually follow that train of thought to its logical conclusion, you will see that you do not get linear, you get a curve. And in fact, you will get Amdahl's law constant in there that's less than 1, and it's still linear, because it's not linear. So if we have a unit of concurrency, I'll also use that very consistently. That's the number of things running at a time, and it's to the bottom of that equation. All right, so it's handy to start with 1. So x is the symbol for throughput. So x at a given n is equal to some constant of slope of the line times 1. Then we get some serialized portion, maybe at the beginning, maybe at the end, maybe both. So I've notated that with gray here, and you see that now some portion of our process equation with a serialized fraction. And I'm using the universal scalability law's notation of sigma here for this serialized fraction. And 2, 3, 4 nodes. So that's what it starts to look like. We start to level off an eventualization. That's exactly what queuing does. Queuing is when access to a resource is restricted and you have to wait in line. That's the definition of serialization. So although these are in a little bit different domains, and it's a little... I mentioned that there's an asymptote. When we kind of take this limit to infinity, what happens if you kind of cancel out? No matter how small we subdivide that thing in the middle, our test can't run faster than 5% of the original. So that curve is going to level off. And hopefully you agree with me that this is not going too deep, and we can all see how this turns into not only imperfect in that there's some serialized workload, but when one of the threads or processes has to coordinate with another one, ask it for some data, they both stop working. I've added as much runtime to the end as the orange takes out of the middle because they had to pause. So the service time of these tasks actually increases. This is not queuing. And this gets really bad really, really fast. Because the worst case explodes really fast. The worst case is that there's n times n minus 1 pairs of interactions between these tasks, which grows order n squared. And I'm going to take that n times n minus 1 and put another component in front of it, a fraction in front of it, and put it onto the bottom of Amdahl's law. And so this crosstalk, Neil Gunther, who created the universal scalability law, calls it coherence. There's a couple of other terms that will float around, coordination penalty. And what happens is that not only does our curve, so we get retrograde scalability. And if you think about this, you've probably seen this a lot in system benchmarks. Many system benchmarks like cluster databases and things like that, that you will have a number of workers and some powers of 2. So you'll have like 1, 2, 4, 8, 16, up to, let's say, 256. So you have to kind of be careful with looking at the horizontal axis, really just trying to stop the degradation and show that their system will flatten off and then not deteriorate in performance past some point. But if you look at those and you kind of translate performance of you ask it to do more work and it stops getting more work done and it gets less work done, is explained by that last. And you can drive some sliders around and just see how sensitive this is. The cost of the design for scalability. So when you probably linear scalability, we made it highly sharded and we can grow it infinitely. Well, you may be able to grow it infinitely, but they may not have any fixed capacity limit on them. But what happens is that as you grow them, you will start paying a huge amount of overhead, and you get this diminishing return on investment. We can take a couple of metrics. So last night, I grabbed some metrics from one of the database servers running in our system, and there's a variety of I can tell from the relationship between these two things. Can I predict the next presidential election? Probably not. But what I can tell you to do is just scatter plot. And the axes on this scatter plot are exactly the same. Is it linear? Looks pretty linear, right? How many of you would kill to have a 97.8% per square, right? There's a lot of data scientists and data really obvious on this chart is that line is not pointing at 0, 0. And that is the first data point in every linear. And usually when people look at charts like this, or when they plot charts like this and say, see, this is linearly scalable, this is kind of, the justification for that conclusion. Problem. All right, so we have one vote for problem. Do we have any votes for, the system can actually scale quite a bit further? I see a couple, yeah. All right, so let's see how it goes. So, how many of you want to change your vote? This is actually a highly nonlinear line. At the right end, the points are below the line again. This is what this system's scalability really looks like. And this is actually pretty clean. These points I took, I said I didn't. Each of these points represents a fairly decent amount of time. You know, it's an average throughput and an average concurrency over whatever 10 minutes of time. And so the system is actually behaving fairly cleanly and fits very well to the other points to really give us some room to fit. So if you look at the concurrency range in which to fit. So how much headroom does the system have? Maybe we can get twice as much work done from this system or something like that. We look at this and it starts a little bit less exciting. You know, the way that this chart is plotted, there's actually chosen to put the axis range. I could have made that go out to 1,000. It would be sort of an Edward Tufte faux pas, right? Lying and saying, see some lines on the chart and going, how much headroom is there? And the reality is, stop really giving us any payback under increased load. And the bad thing about this, performance is going to go to hell. It's going to get highly variable. It's going to start stalling. System past the threshold where it gets stuck and turns into the spiral of death, and it's the kill-9 territory. We looked at shorter-term time averages that would reveal more of the variability that's kind of averaged away in these points. Most likely what we would see is that cleanly probably turns into more of a hairball kind of thrown on the screen. All right, so we went from, wow, it looks pretty linear to I'm kind of worried about this system approaching the limits of its capabilities in, a couple of simple moves. All right, so that I think is actually pretty transformative takeaway for capacity planning, where capacity planning used to be just sort of hard, insanely hard, queuing theory analysis and things like that. You know, we've just taken two simple measurements from our system, throughput and concurrence, but we can do something really interesting. From the outside of this system, treating it like a total black box, we can actually peer into it like an X-ray and figure out what's going on inside there, even without knowing anything about the internals of this system. This is fairly easy to do. We can answer the question, what is this system's primary bottleneck? There are two kinds of bottlenecks. There is that serialization penalty, where we get nonlinear scalability, because of things making each other do extra work. So these parameters in universal scalability law have a very something like that. There's a real physical model that this all comes from, and a theoretical basis behind it, and it does work. All right, so I've listed the physical meaning below here. The throughput of single-threadedness, that's the slope of our line. We've got something. What you're really doing is getting estimates of the parameters. So by progressing against these points, we're getting estimates of how much serialization and crosstalk there is in it. And this system's parameters are plus or minus 7.5% of serialization penalty and a very, very small fraction of crosstalk. Okay. There are other systems, if you click through in the references at the ends of these slides, there are lots of in a Node.js system that is single-threaded, and lots of things are waiting on single-threadedness. You might see things that have a lot of crosstalk penalty in spend a lot of time in thread scheduling and things like that, or in the internal cross-thread communication. And so you can see that really clearly when systems, and its bottleneck is probably mutexes. Just an internal implementation detail of the database server. But it gets just very nicely kind of teased out. We separate the wheat from the chaff and we go, if we want this system to scale better, to give us better performance, the one thing that we should be thinking about is how could we reduce the contention penalty over serialization? And it might be at the operating system level, it might not be the database server, from just taking a couple of metrics and doing a regression. I know it kind of blew my mind. Let's scan the QR code. You can get these slides. I'll leave that there for you for a moment. But the next slide after this has some references, and you can answer the rest of the questions there. Yeah.
Question for those coefficients again? Where they're coming from?
The intuition for the coefficients. Okay. So the gamma on the top, all of the components disappear from the denominator, and you just get, it reduces as the slope of the line. Gamma is the line that goes from 0, 0 through concurrent. The intuition for Amdahl's law is a little bit difficult for me to explain kind of verbally, but the idea is that, but it does, when you rearrange, is the n times n minus 1 number of potential interactions between things doing work concurrently.
So you can chase Baron into his office hours if you want to chat with him more. Unfortunately, we're a little short on time. Office hours, you can have some copies of his book up there. And one more super important announcement, our printed schedules did not arrive. So that's why you're all wondering, where do I go next? What do I do? What the hell is going on? Who's running this thing? We have lots of volunteers around with data shirts who can help use NYC. And if you go there, you're going to go to our website. It's going to show you all 3 sessions that are going concurrently. Right up here, this is the DataEng track room. So any talk that's in the DataEng section of the schedule will be right here. So DataEng, lots of great talks today. Enjoy. bit.ly/schedule-NYC.
How much of that was
more deeply, so we can track what a model, what's the code running for a given model running in production. Now we also want to expand and make it easy to create custom environments for your notebooks. Let's say you just care about certain types of libraries that no one else does, but you want to quickly start for users to register new base images. The way we design the system is we have the API layer that is highly pluggable, and you can push new images that you want to register as software environments, or you want to push new hardware configurations as your hardware resource options. Users can also, basically, everything will scale out on very high memory or multi-GPU instance. So that kind of flexibility, like, people really love it, and they don't have to worry about closing their laptop and losing the state. All those problems are gone. So it's kind of eliminated the need for local development completely. We also provide code syncing tools to make it easy to develop in your favorite editor, and then just continuously sync your code into the Kubernetes pods. That was one of the big asks that was blocking a lot of people. Not everyone cares about developing into their notebooks. They want to be able to use their favorite editor. So that was, I guess, like one of the biggest features that moved people away from local development.
Other questions?
Yeah, thanks for the talk. I was curious, do you have also engineers using this, or is it just data scientists?
Yeah, that's a good question. So as I said before, we have multiple layers, multiple tiers of users. The researchers are less programming oriented, more on they care about the machine learning problem more. They don't want to get into details. So the UI solution is used heavily by the research scientists. The engineers seem to prefer to use mainline tools. So we have a ton of engineer users. I think that we're using mainline tools more than the UI. One other thing is, in Lyft, from the beginning, we've had a distinction between a software engineering role and an ML role. So those distinctions are getting more and more merged now. They're going away. So we see more engineers using the ML tools now. Yeah.
So do you still have like a productionization step where like there's the development of it in a Jupyter notebook, and it seems like this could actually like automatically spin up a service that could then be hit for production, but do you still have like people taking a model developed by the ML researchers and like productionalizing it and making it faster?
I think that's a common problem we were seeing a lot in the past. We actually have the ability to directly spawn Kubernetes deployment based on the model you generated using and it calls the predict method that I talked about earlier. However, we're kind of putting on the back foot and trying to better integrate with CI and Jenkins and deployment pipelines. So we have good traceability of what code's running for a web service and how to roll that or being able to inspect what's running inside that code. So we want to tie it closely to GitHub commits. So right now, our way of doing that is just data scientists will push the code to GitHub, and we're working on making it really easy to use the CI process at Lyft to launch production services from that. And we generate automatic monitoring, and we manage the SLA for rolling out those models.
All right, if anyone has any more questions, Saurabh's going to be upstairs in room 302, elevator right over there. Otherwise, we're going to have William Nelson up in just a couple minutes.
Thanks a lot.
We're going to get started in just a minute, so everyone find a seat.
We're still cracking the beer. Research.
All right, everybody. Next up, we have William Nelson from Intent, and I guess we're on a data modeling pipeline this afternoon, so enjoy.
All right, hi everyone, thanks Dominic. First of all, let me thank the organizers for once again putting together a great conference. The talks have been fantastic so far, and I'll do my best to answer this session so far. The last talk was actually a great intro to a lot of the stuff I'll talk about. So let me kind of jump right in. I'm going to talk a little bit about Intent Media, the company I work for. We're a startup based in downtown. I promise this first section isn't a sales pitch, unless anyone's a chief marketing officer, in which case it's definitely a sales pitch. Afterwards. What I want to get to is kind of an understanding of why machine learning is really important to us, right? And why the data science is really core to what we do. And then some of the motivates some of the problems that we face. The two kind of actual things I will talk about, one is a Scala library we built called DoubleSpeak, which is really around feature extraction, and kind of why we built it and what it aims to do. And then this kind of very natural pattern of you solve one problem and it's really successful and it leads to lots of people using it and that leads to other problems. So the next one was about having to deal with thousands of models that get changed very often, so how we had to automate the pipeline. Okay, so first things first, credit where credit's due. I didn't do a lot of this work, but there was a core team. There's a lot of other people around the edges, but I think these are the people who really did most of the work. And all the heavy lifting was done by Joaquin, Gabriel, and Sebastian in particular. Some of this is Sebastian's brainchild. So if anyone has any really deep technical questions, see me in the office hours, and if I can't answer them, I'll give these guys an answer. You, John, and I are the data scientists, and like good data scientists, our role is mostly to like poke our noses in once in a while and make things extra difficult for the engineers. So, introduction to Intent, who are, what we do. So the basic premise of what we do is founded on the idea that almost everything on the web is optimized for the average user. And just like there's no such thing as a family with 2.4 children, but there isn't really an average user. But that's the way the world works. It's the way everything in our life works. And we could undo that. If we could start optimizing for individuals somehow, we could do better. And you do better, hopefully, for the website, doing whatever your business metrics are, but also for the user. You start to get treated more like you want to be treated. That's obviously a super great lofty goal. It's great to say, but what do we actually do? So what we actually do is we've built a predictive intelligence platform, which basically scores users real-time on a site. And we return an intent score, which is something between 1 and 10, which can mean various different things. There's no surprise to this audience, this is machine learning, this is the data science. And one example that's very common in a lot of our partners is what's the likelihood that this user is going to purchase your site, right? That seems to be something most people care about, especially on the e-commerce side. So this is a kind of a good example, but it could be various other things, like likelihood that they're going to shop somewhere else, likelihood they're going to book this other thing, likelihood they're going to bounce, likelihood they're stay on the page, and so on. I should say that, like, 10% is good, but it definitely doesn't get you from the whole population down to the individual. It's a step in the right direction. So, like, it's allowing them to kind of treat users differently. That's kind of what we're getting. So the types of experiences that our partners are commonly using this for, imagine it was like a prediction was likelihood to purchase. Then if you're on the extreme high end of the scale, you give users a very commerce experience. They want to book, you just keep things out of the way, keep it clean, and get them straight to the car quicker. And on the other hand, if they're not likely to book, then they maybe want to do something else. Right? Maybe they're still searching, and you want to treat them more like a search. And the media in our business was kind of where we found it, so we kind of provided that in order to a lot of the revenue comes in. And so you can kind of start to target the ads to the people who are most useful. This is just one example, right? There's lots of other use cases you can start to think about, and actually there's a lot of partners are starting to get really into slicing up the data in different ways by these scores to do different types of things. Who do we work with? Well, we're definitely in the travel vertical for sure. We've got pretty good coverage in North America and Europe, and we're expanding out Latin America and Asia Pacific. And the only real thing to take away from this slide is that we have a lot of searches, right? So we make these predictions a lot. So it's approaching 1.5 billion searches a month. Each of those searches is multiple events which have multiple predictions. So this is really something that happens at the web scale. So that's intent media as a kind of concept. How does data science fit? It's like, where does it come from? What do we actually do? So the data we use is collected from our partners. And so that's either a JavaScript tag on the page or a pixel that's dropped on it that fires events back to us. Those events are logged, and that log data is what we train on. So we'll train a model. So the example of prediction, like that. These models are then used for real-time predictions. And when we say real-time, we mean real-time in the sense of page load time. Right? So there's obviously all networking effects. You've got to get this score back to the page and so on. But for just the predictions, we have an SLO of 10 minutes. So these predictions, the real-time inference has to be fast. It also has to happen at high scale, high throughput, right? So we're peaking out at about 160,000 a minute, and that's growing really rapidly over the last 12 months. So this has to be sort of very horizontally scaled. Once you've made the predictions, various things happen. One growing use case is we just pass the prediction back to the website and say, like, hey guys, do your UX based on whatever it is you want to do. We've got the data to do it. A lot of our partners, we will provide certain UXs based on that experience for them. So we'll show ads to the right people, or we'll show conversion experiences, maybe get a promo code. And then in addition to working out what type of UX to show, then like there's subtypes, so which type of ad you see, which type of promo. Those are all sort of decisions that have to happen in real time. And the real emphasis I want to make here is that this is all what powers the business, right? None of intent media would be possible without this. So it does sit sort of the very core of what we do. Okay, so background stuff aside, the thing I want to talk about first is a Scala library we built called DataEngConf, and it does feature engineering. So one of the challenges we had was building and testing features rapidly. We want to try out a feature, we want to see if it works, and get it out there. And I'm going to talk you through how we do it now with doublespeak. And I'm also going to point out a problem that comes from versioning features and trying to serve models and publish models in real time. If you've done this before, this is kind of very familiar. If you just haven't done that publishing step very often, it's something you might not have figured out. So when you think of feature extraction as a step in a modeling pipeline, what do you want it to be? Well, the software engineers in the room are going to want it to be robust. Right? We live in a real messy world where data comes in, it's incomplete, you've got nulls all over the place, right? You want to make sure it's robust to all these things. It should be production level code, right? It shouldn't be something that like I as a data science, the data scientists have hacked together in 10 minutes and I'm going to put it up there because it worked on my laptop, right? It needs to be core code, so it should have all the things you want. It should be maintainable, it should have continuous integration. On the other hand, as a user, I definitely want to be able to use quickly. Right. The whole point of being able to do this is to rapidly experiment and get things wrong 10 times, but at least the 11th time it works. Right? And if each one of those times takes a month, this is wrong. It should be flexible so that the types of events that we're getting, I don't want a different feature extraction for each. I want to be able to like reuse the code I use over and over again for different types of different types of events. And I want it to be feature rich because at the end of the day, I don't want to have to deal with interpolation by hand every time. Right? I'm used to using sklearn, which has all these fantastic features in there, and I want all of them. Those two things are very different sets of requirements, and actually finding one that does everything together is surprisingly challenging. But the other thing that's challenging is making sure this works fast at inference, really fast. So we built doublespeak. So doublespeak is a Scala library. What it does is define a feature extractor set, and I'll talk a little bit about what that is in a second. And you can use this basic object to extract features from RDDs. So if you're not used to Spark or Scala, RDDs are one of the distributed data systems they have. But it can also be used for individual records real time. And the key point there is that you can use it to extract features from individual records without Spark. So you don't have to build Spark into the section. You get some things for free. Free in the sense that you already had to do them, so you can as well output it. So you can encode all the features from batch jobs, and you can see what those are like. You get all these feature summaries, and you can see how often certain categorical features appear, the averages and stuff like that. This is very much like the dot describe. So I'm going to show you some actual code. When I say this is easy to use, I really mean it's easy to use because I'm the barrier, because it's not easy enough for you to use, and we have to fix it. And it comes with a whole load of all the things you want, like imputers, transformers, normalization, and stuff like that. And actually, almost all that's built in as defaults that you can never provide. And it leads to very concise code. If you haven't seen Scala, just read this as pseudocode, you don't need to see the details. This is the basic object to be built. Okay, so it's a feature set. Scala is strongly typed, so you have to give it a type of the object it's going to apply to. So in this case, it's impression. It's just some object that kind of contains the data you're going to pull your features from. I gave as an example this validators thing here. Actually, is to have the single value as a default, so you can ignore it. But you can put something in here that says, ignore features that have this block. So there's a feature you get, always the same value in the training set, just drop it. There's too many nulls, get rid of it. And then on the next 3 lines, we've got 3 features. The first one's a categorical feature, it's a numerical feature, it's a binary feature. And all you need to define is the name of the feature, and the second argument is the function that returns the value of that feature. As an example, to explain kind of what else is available if you wanted, you can override the default transformers for a categorical and say, well, how are you going to encode this? But you don't need to. And you don't need to specify normalization. In a single line, you define a feature extractor and how does that feature belong. And it really is that easy. So if I have an idea for a feature, it's 1 line of code. I can write it down in that. Some nice features about this. Some of this is to do with doublespeak, some of this is to do with Scala. But one thing that's very nice is being strongly typed, it means it's very robust to schema changes. So if someone changes something about the expression type, someone changes, I think earlier we talked about int going to string for some element of it, or some adds an element or removes an element. This will all fail at compile time, so you don't have to worry about runtime. It's robust in another sense, having categorical that you a value for a categorical that you see in real time. You didn't see in the training data, you just default to this other category. That's actually how you roll up a lot of long tail categories. That long tail is big for us. We have a lot of categoricals that are extremely high cardinality. So you can think of like airport codes. There are tens of thousands of airport codes. If you think of origin destination airport codes, then we're talking about hundreds of thousands of categories, and that has a very long tail. It has all the kind of default encoding and interpolation and normalization if you want, so you can just use it out of the box. You don't have to like start putting in stuff by hand, and you automatically get these feature summaries, right? So, and I say automatically in the sense that it has to calculate things like the mean and standard deviation to be able to do normalization, so you may as well output them and be able to see. Gives you a way of debugging features quite efficiently. So that was like the one piece was just this feature set, and sort of said this is the core to it. How does that actually, like, what does it look like if you're using it for something real? So the color coding here is anything that's red is doublespeak, the rest of it's just bog standard Scala. There's nothing special about it. So we defined this feature set for these 3 nice little features, and that was the basic thing we needed to do. What we're going to do next is load in an RDB of these basic data. This is your training data you're going to test on, or you're going to train on. And then there's a doublespeak function called RDB extractor, which passes features into. And that can apply to an RDB. And what all it does is it produces for you an extractor object which has in it a data frame ready for use in provisions, or ready for you to train. So the last 2 rows are just taking that training data set, joining into whatever your labels are going to be in the train. So it really does kind of fit very nicely with the ML-lit world. So this object, this thing that we get, this RDB extractor, what's in it, right? So there's the raw features. That's really just if you want to look at them, kind of do some analytics on it. It's kind of useful sometimes to say like, hey, I've got this complicated, sort of, structured object, like an Avro object or something. It's hard to reason about it. I don't need to data frame. I can do this cool analytics with it. The reference features are the thing that you actually plug into the training machine. It's just basically got this features column at the end, which is the vector, the feature vector that you're looking for. For this example, I turned off normalization just so that you can see how the one-hot encoding works, but you get the picture. This is just the features column that you're looking for. The other thing it produces is extraction metadata. This is all the things like what categories did I see for a particular categorical? What was the encoding for it? What was the mean and standard deviation if I'm using standard normalization for a particular value and so on. And those are nice to have from a kind of debugging point of view, but they're actually necessary to be able to test and do inference with. So let's see how that comes later. So this was the training. How does it work when you want to test it? I test it with batch testing. So it's almost as simple, right? You have this object, there's a .extract function or a method on it which you can apply to other data. The key point there is that this extract method uses the original categorical, the original normalization for training data. And this is where you get things mixed up. Kind of not concentrate. This is where you can accidentally only use categories that exist in the test data. So that's super easy. The whole purpose of doing this was really to focus on the real-time inference. So how does it work in kind of real time? One of the things we wanted to avoid was having to have a Spark dependency in the real-time world, because it really feels overkill to have a single event come in one at a time, load that into the Spark object, spin up the whole Spark sort of dependency, and then just do a single. So it's almost as simple. You will load this metadata, which is this sort of artifact that we had, that gets loaded into the model. Okay? We'll talk about how this model gets published and the metadata goes with it in a second. And from it, you can apply a record method. Right? So this is just for a single method, a single record. I want to extract features. And that is something that's built out of that metadata. And once I have that, I can apply a single impression. I get whatever it happens to be a vector. And that vector is ready for pushing into a serialized model. Cool. One thing, and I don't know where the link is, somewhere in here is linked to a Spotify code, open source code, that does something very similar called featuring. I highly recommend everyone looks at it if you're interested in any of this, especially since that is open source and this is not yet open source, so not much of a choice. I just wanted to point out the kind of key differences. So first of all, the featuring code is much more feature rich. They go into a lot of natural language stuff. We have a lot more features built into it, so it's great. This was geared much more to getting real-time inference stuff. So it's super fast. That was really the core to it. So, when it comes to, we're discussing open sourcing it, and it'll be a discussion next year as to whether it belongs as a separate thing or whether it's just additional functionality. So I want to kind of emphasize how successful this was as an engineering product or an engineering effort. So the old way of doing feature extraction was like just building the functions and testing them extensively, and then having it there, and then once you've got one, you've got another one, and trying to wrap them all up together and trying to make sure all the vectors are consistent and so on. Which was painful, right? We ended up having about 10,000 plus lines of feature extraction code, and when we translated that all into double speak, just the same features, it went down by one magnitude. Bigger, and more importantly, the number of test lines of code that we had to support those features went down from like 45,000 plus. I still don't think we had proper coverage, down to like less than 3,000. And that gets it small enough that you can get your head around it and you can kind of really reason about, are there big gaps? Is there anything we're missing? Are there any edge cases we haven't covered? And as a user, by far, the biggest thing was to get a new feature into production went from an effort of days to weeks to minutes. So I can code up a new feature that I've just decided, hey, I think this is going to be great. And assuming I've done some analysis, I think it's a good idea. I can kind of one line of code, commit to Git, the whole continuous integration process happens and it can be pushed to production. Which is amazing. It's exactly what we want. Really fast experimentation. Try lots of things. Some of it's going to stick. Which is fantastic. However, it leads to this massive headache from an operational standpoint. And the headache is now you've got lots of people like me changing features all the time. So the models are constantly changing. And so you have to deal with that. And you have to deal with being able to publish, deploying models very rapidly all the time, and making sure that the model versions and the feature versions are in sync. And that's something that, if you get wrong, you get very wrong. So let's talk about that. Let's talk about what happens when you think of features. Offline train some features, build some features, train them on, and then want to deploy it. How does that process work? So typically, these are the steps you think of in an offline training world, right? Load some data, extract some features, I train a model, I'm going to do various things to test it, validate and stuff. But assuming things are good, I'm going to push that model up to production. And in our case, prediction service, dealing with the prediction requests. The two steps, extract the feature and train the model, are distinct steps usually. Right? And they're certainly similarly the distinct steps of the real-time world. You need to find the right model, and I'll talk about why we have multiple different models in a second. And you better extract the right features for that model. And in case anyone hasn't thought this through, I'm going to do a really trivial example of why this can go wrong. So imagine you have the blue model up in production, it's constantly serving, it's good. It happens to be super trivial, it's got 3 weights, or 6 weights, and it's expecting 6 vector. I never give it a 6 vector and make a prediction. Meanwhile, in the offline world, I've retrained the model, and for whatever reason, I now have a model that only takes 6 weights. Maybe I've lost a category, a categorical. Maybe for some reason I decided I need to use a feature, and I don't need that feature anymore. Now I've got like a feature extractors that will produce a 5 vector and a model that's expecting a 5 vector. And in production, in currently serving models system, I have things that are expecting the 6 vector. And you see immediately that the only way to push this to production is to make sure they're always in sync. Because if you ever try to do one first and then the other, you're going to end up in this period where something is just not consistent. Right? You're either giving it 5 weights and a 6 vector, which, I mean, if you make things robust, isn't going to fail, but it is going to produce nonsense. And that's kind of worse than failing, because it looks like it's a prediction, it looks like it's working, but it's actually just and that inconsistent state persists until you manage to push out the version of the features that go with the model. Now, this kind of deployment problem wouldn't be the end of the world if it was like one deployment, happened once in a while, and it was only going to take like a few seconds to go up and be like, okay, it's a few seconds of inconsistency, but it's something we can do. The challenge we face is it's not once in a while. We have thousands of models and we deploy them every day. And that little bit of like inconsistency during deployment can be like absolutely critical. So the key takeaway here is you really do need to keep the feature extraction and the model that you trained in sync, right? Those really have to be part of the same process. They can't be different. And so doublespeak helps us a little bit in the sense that the feature extraction code is all static Scala code. So when we deploy something, all that feature extraction logic goes with it. And the only thing that's left that you need to load is the serialized model and the accompanying metadata that the feature is built on. So as long as you keep the metadata and the serialized model together, now you can be sure it's going up consistently. Now that's not super trivial, right? But at least it's kind of encompassed what you need to keep together in a very concise way. And it's all serialized, so you don't have to worry too much about different pieces of code getting in. Okay, so this is kind of one half of the talk. This was all on the feature extraction side, and the kind of library we built to kind of help us do this. One of the challenges that we were facing before all this was a proliferation of models, right? So we were going from like originally 10-ish models to hundreds of models, or now thousands of models, and all these models were trained. So, load thousands of models, they all get kind of configured by hand. Once they're done, you schedule them and they go. You can kind of keep track of that as a group. But when you do that, and then you've added on top of it that that number is growing, and all of them are constantly becoming very different because people like me are adding different features and changing features, it becomes a configuration nightmare. Just keeping track of what models are where, what partner used what model, what the result was. This one failed, and I don't know how many days it failed for, and I don't know what was actually used to make the prediction. It becomes a real challenge. So why do we have lots of models? That's the first question. Why don't we just produce one model and predict on that? That was all. So unfortunately, we don't live in that world because each of our partners, we need to train a model for them themselves. Partners are usually pretty stingy about sharing data, so they definitely don't want different people getting to model training on their data. So every partner gets a model. And that first slide where you saw lots of partners or whatever it was like 300. So I'm like, cool, 300. I mean, okay, that's a lot, but it's you can deal with it. The real problem comes from the fact that not every partner gets just one model. So each partner could ask for a model for, let's say, users likelihood to purchase a hotel when I see them on my flight. And that starts to explode pretty quickly. It gets even worse when they say, like, oh, I want that, and I also want to know, like, what's the likelihood that they're going to bounce? What's the likelihood they're going to have another page view? What's the likelihood they're going to do something else and something else and something else? So the number of these models kind of goes up combinatorically with the number of partners, the number of different products, the number of conversion products, the number of models you're trying to set. So we have thousands of data. If they were all qualitatively the same, that wouldn't be the end of it. If there was kind of one universal set of configurations you could use, right, the rest of it becomes a schedule issue. Unfortunately, that's not the case either. So you can totally imagine the amount of data you need to train a model is going to be very different from the Expedia of the world to some small European site, which has very low volumes of travel. So there's some like cleverness you need to do to just work out what's the right amount of data to use for each model. But it's something you can kind of get your head around and figure out what to do. So that's kind of the length of the training data. Different models actually use different features, right? So now we have like really distinct models that are very different from each other from a kind of functional point of view as well. They have different objectives, right? The different model types we've been talking about. This is what Expedia considers a purchaser involves some implicit look ahead. Right? A purchaser when? The next 24 hours, the next 10 years? I think those are very different things. And different partners have different definitions. So actually, almost every part of the model is different for different pipelines. And then finally, different algorithms, right? Maybe you try a single model that works pretty well, and something like logistic regression is perfect, obviously use the simplest one. When it doesn't work, you're going to use something smarter, like you've got to go to like a gradient boosting tree or so on. Like whatever it happens to be that works, that's the one you're going to use. But now you have lots of different algorithms that you need to keep track of as well. And if all this was a one-off for each of these things, that would just become your day job. You do this every time, push models out, and never change. Good, keep you busy, but very pleasant. But the real killer is that all of this has to repeat every day. Right? So we don't live in an online training world. We batch train and publish the models, and to keep them fresh, we retrain every day. Which means we have to worry about the deployments, thousands of models every day. And so the challenges we saw about publishing models and getting everything in sync and not messing it up become quite exacerbated. So here's the kind of picture to have in mind, right? We have this kind of standard training pipeline. I'm going to talk a little bit about how we kind of schedule these things and so on. We're an AWS shop, so you can play a game with guessing what the symbols mean inside. So these are the sort of modeling pipelines, and we have hundreds here, we have thousands of them live at any one time. And the basic steps along the way are load data, load the right data that can be different for each of these pipelines. Extract features, the features we're using is different for each of the pipelines. Train the model, the definition of the objective, and algorithm can be different from each of the model. Test the model, the actual definition of what is a pass, what's good enough, can depend very much on the partners. So really the only thing that's common to these pipelines is the publishing, right? Is to actually go ahead and use it. Or not, right? Maybe you decide this one wasn't good enough and you not. So what did we do? Oh, sorry, this was all in the offline world. There's an exactly similar problem on the online side of things, right? When it actually comes to the online world. So this has to be fast and it has to work at scale, so we use ECS to kind of horizontally scale. But every time a request comes in, some things have to happen. So you need to find the model, right? So a request comes in from a partner for a particular product, for a particular prediction. You've got to find the right model for that. You've got to find the right features that go with that model. And you've got to make the prediction, and making the prediction means you've got to remember what the algorithm you're supposed to be using is to make the prediction. And all that has to happen fast. And so these are the challenges. This is why we kind of had all these thousands of things. This is why it became difficult. And so we decided to build something. And one of the reasons I want to just leave you with before I start talking about what the actual infrastructure looks like is the scale of some of these things. So the training is big. I mean, it's not Google big, but it's still tens of terabytes of training data every day. Right? So that's a lot. We have thousands of models live, right? So that's a lot of models to keep track of. It also means when you get into the thousands, you're starting to expect some to fail. You have to work out what you're going to do with those failure cases. The predictions have to be fast. So I don't want to try and pretend that our response times to the website are 10 milliseconds, but our prediction response times internally is 10 milliseconds. That's our estimate. And we have to deploy, essentially 100% of our models get redeployed daily. The only exception to that would be ones that actually get deployed faster than that. So if something changed with the program, you want to deploy in addition to the daily. And the last thing is all this has to be very robust because this, a failure to make a correct prediction is kind of a really bad thing in the context of what we do. So you can imagine you're a partner out there and you decided you're comfortable serving ads to people who are predicted to be low value. We start predicting everyone to be low value and they start seeing ads and they're about to make a purchase, that's going to really hurt. The other way is just as bad, right? If you start saying, hey, all these low value people are going to start getting conversion listing experiences, that's just a total waste of time and effort and money that you're not going to want to spend. And if our partners have integrated these scores and put it into their sorting algorithm or their search results, or they're using it for email retargeting or whatever, they start to go very wrong very quickly. So we need to be quite robust and make sure that we're always serving whatever is the best prediction we can. And also understand that if we can't serve a good prediction, we know what to do about that. So this all prompted dealing with a modeling roadmap pipeline. This is something we're kind of working on this year. and we finished it up now, but like the system prior to that worked, and it was consistent. It was just extremely painful. A lot of pager duty stuff going off, and kind of like several teams sort of hold off trying to keep this sort of modeling automated pipeline is taking most of that manual effort away from us. So we use Airflow. It's funny, I was expecting to have to try and convince people why Airflow is a good thing, but it seems like every third talk up here has used Airflow. So Airflow is great. I suggest everyone uses it. If it hasn't used it, take a look at it. We use it basically for the core scheduling and just coordinating what's going on in different steps. One interesting thing we found is, we have thousands of models to train, and that's a long way from every possible model. But the coordination effort in trying to decide which models are going to go and what happens, someone wants to add a new model, and the account manager comes in and says, I want to tweak this model and so on. It turned out just to be easier to train every possible model that's supported by the data. And that leads to compute overhead, right? So we're wasting money on AWS costs, which makes AWS happy, but it actually saves us a huge amount on the tech ops side, and it warrants the expense. The other benefits are it just means that if anyone wants any models there. And I'll tell you a little bit in a second why we split these up into cohorts of training jobs. It's very practical reason. Anyway, the first step in this is this prep step, which is basically, okay, go build up the jar, which is the latest feature versions, the latest code, this thing is going to get deployed. Stick it up in S3 so it's ready to use. It also goes and looks at our data warehouse and says, okay, what data do we actually have? The last X number of weeks of training, how many of the events that we're going to train on did we see? How many of the objective events did we see for every site, every partner, every combination of things, or which ones of these is actually sufficient to build a model? And then go ahead and train those models. So once we've worked that out, we split these things up into cohorts, and the cohorts is really just to try and get like a roughly equal-sized number of training jobs to go and retrain as well. And then launch those training jobs. So we use Amazon's EMR, the Elastic MapReduce clusters, and we just basically, for each of these modeling jobs, we spin up a new Spark cluster, train a model, and have the outputs pushed to S3. The last thing then is the publish step. And the publish step is, if everything works, it's true. Everything works, it's just go ahead, push this thing up to ECS, the jar up to ECS, multiple versions are ready, and everything's being versioned and kept in the same. The only logic that's required here is actually very important logic, is what happens if one of them failed, or some model didn't reach some validation threshold and wasn't good enough. So for example, what happens if Expedia Japan hotels fail? What's the best alternative model to use in that case? Is it Expedia Japan flights, or Expedia US hotels, or some totally different model that seems like unrelated and turns out to do very well? Or is Expedia Japan hotels just so important that we should fail out completely, stop the whole not deploy process, fix it, and find out what's going on? And that logic is all kind of being encoded into this like publish step, so we kind of have hierarchy of fallbacks and so on. So here's what the whole architecture looks like. Like I said, we're an AWS shop. We use Airflow just really kind of kicks things off and coordinates and keeps track of what's going on where. Snowflake's our data warehouse. It's great so far. It's a real cost saver for us. So the steps along here are, the first time you hit Airflow hits S3 is where it publishes the jar. Sorry, it wraps up the jar and pushes it up to S3 so it's ready to be used by EMR. It then kicks off a whole series of EMR jobs. And in theory, you could just go, here are my 4,000 models I want to train, go train all of them, and spin up 4,000 EMR clusters. It's a good reason not to do that, so instead we do it in chunks of roughly equal-sized jobs. Each of those goes and reads the jar from S3, does the training, does the testing, does the validation, and then pushes the artifacts back to S3. Airflow then comes and says, okay, it keeps track that it's happened, these ones have finished, the next cohort's ready to go, it pushes up the next cohort, and it goes through the whole training process. And all the results of these things also get pushed to Dynamo. That's really just for on-once. It gives us a kind of persistent view of what model happened when, what feature versions we used, what the feature summaries look like at that point, what was the accuracy, and so on. As well as the decision about whether or not this model is going to be used, and if not, what was the other model that was used in its place. So this is the kind of governance piece of it, so that we keep track and go back and say on Thursday last week what happened. And finally, the publishing step, we just go and deploy this jar up to ECS, and all the model versions and everything with the corresponding metadata features are in S3 ready to be cached out. And this is the piece that kind of keeps everything in sync. The main key point here is Airflow will fail the whole process if any piece of it needs to fail. So if some really important partner or some really important model fail, we're uncomfortable with publishing that, without having that model up, the whole deploy fails as a consistent, or at least as an atomic deploy. Just as an aside, we also have this ability to push that same code to lambdas. We use lambdas quite a lot. And they're great for small-scale experiments. And so if you wanted to push the code up there and then you wanted to test against some small slice of production traffic, basically as a last A/B test before you go live with something, this is a very efficient way to put something up and tear it down without influencing the rest of things. We did toy with just using lambdas for everything. It works. It's effective. It's just quite possible. The NYC system. Okay, and I think this is my last slide. So just some things to kind of keep in mind about what we like about this. So one actually that really relates to the last talk is that this is the production environment. This is the production code, like the production infrastructure. But as a dev, I can toy with something and I can use any piece of it. So all Airflow is doing is saying, go trigger this thing, go trigger this thing, go trigger this thing. I can trigger any of those pieces myself. And we have staging environments where you can spin up the whole end-to-end thing, and you have dev environments where you can push up anything. So if you want to do an ad hoc review run somewhere and see what happens, you can totally do that from the machine. You push the lambdas, which is nice to have. The key one for us is this will automatically infer what the correct model configuration to use at least as much as possible. Right? So the right amount of training data to use and so on is something that can be automatically inferred. And a lot of the other configurations that go with it are just dealt with by trying all configurations. It's kind of like the hyper-parameter tuning version of this. We define the fallback logic. That's something that's the business logic that we have to put in place. It's defined, and it's kind of defined in one place, which is nice. And it also guarantees that every request will get a response. And that response is the best one we can give you at the time, and we know what happened, what that response was coming from. So I promised to explain why we break things up in cohorts instead of just spitting out thousands of Spark clusters on EMR. The main point is EMR is a shared resource. And AWS throttle you can do too many. That would be fine if we were the only ones getting throttled. But meanwhile, our data pipelining folks also use EMR. And getting throttled as a company is a pretty good way to get unpopular quickly. So keeping the number of jobs you're spinning up to a manageable size is a good idea. It also improves maintainability. So if you start to see problems, you don't have to worry about spinning up the rest of it. If the first 6 fail in a row, you may as well not carry on with the rest. The key point here is this is a persistent, we keep a persistent, consistent record of every model, every feature and everything went up, so that we can always go back and look at it. Actually, one of the things we're building right now is just making that nice, this nice integration from models, alarms that go off, and some nice visuals and so on. And the key point I want to leave you with is this is a way of making sure that the deployments are autonomous. Right? If anything fails or you decide it doesn't meet your business needs, you can just fail the whole thing, and you don't end up in some weird state where some of the things are predicted on the old version, some of the things on the new version. Okay, I think that's all I have. Back to the question.
All right, thank you, William. Who has questions?
I'm still a little confused by what you mean by train every possible model. So is that you have hypothesis A, hypothesis B, you test them, they both seem okay, and you productionalize both? Or is it oh, you have 6 features for a model, and then you can train for every permutation of literally those 6 features?
That would be awesome. My AWS people would love that. No, we don't quite do every model. That's totally true. When I say every model, I mean, so for every partner, there are a maximum of 4 or 5 products typically. So hotels, cars, flights, and cruises are the ones we have to deal with most commonly. And then there's every possible combination of those 4 and those 5. So there's 16 combinations of things for each partner that we have to do. Not all of them may be actively used, but it turned out to be easier just to train all 16 models and only use 3 in product, only serve requests 3 than it was to worry about which of the 3 you can use for this one. So when I say every model, those are the configurations, not the features.
Other questions? You can just use that mic right there.
When you say the model,
you say the binary object, or do you say some like text instructions or something like that?
Yeah, because you know, we serialize models. So what goes up is a serialized model, and then what comes out of the record feature extractor is a serialized feature list. Yeah, actually, we don't try to deploy the model. Actually, that would be extremely difficult for us because all models can be different. In the old systems that we had, that's kind of what happened. The model was part of static Scala code that got deployed, so it just same system memory. And that meant you had to use the same features and the same model for every model.
Other questions? All right, William's office hours are going to start at 3:15 in room 302. I think we have a break. I assume there's cookies or something out there. I hope so. Enjoy.
The next is the last sentence. Carol said that they launched it a while before people like this request has been adopted, right? Now though, he said it's like 95% adopted. Really positive. And now that it's adopted by all the things. Apparently the engineers are too, it's just their engineers to lower level basically what they have is it's essentially a web app where you log in, right? It's basically like a Dockerized image of major machine learning, like do you want, pairs, TensorFlow, that sort of thing, and then you basically choose like here's the it would be like if Databricks was integrated with all of these like optimizations, all the libraries. So that's like like where my favorite jobs was but like all you have to do is it opens up automatically where it's on its cluster and you can automatically start like live things on it. They do what's called system where how the priority of like saying okay, here's my config, they can start
But if it's so much target size, what are the pieces here? Yeah, the data science for example. But yeah. Well, it was kind of like a pulse where like you show up and like, ride the whole valley. After compared to that.
So, I would say at that point, right,
If only we could tell.
Was your classes looking at the stats?
Presumably, I feel like if you're trying to say one small sequence, that was pretty consistent. That you're going to be only able to make sense. You can also get contracts tomorrow. I do have to wait 24 hours for the 50 one all the day with our backs on all the time. I'm just like, how much dive could that don't make sense. They're going to figure out whether that's like the mean spot. But then like, oh, part of it is like that's what it's about. You can just skip it. That's what we do all the time. Yeah, but like over the course of months, you skip like several weeks, and it's not a bigger problem. Like it's back to all your document solutions to the problem. And so like, what's that do for?
I think
Correct.
does anybody actually
Nobody shocked them when they're like,
so like do not want this? I don't want
there's a lot of she's one looking. She's one shot.
No.
Okay.
Tuesdays is like And I'm also doing an analyst. So I think she's not that. I don't think she's doing it well.
You should want to do less for less money. Yeah. Or should do more.
Right. I think she can maybe do
No one can see it. Instead of concept.
She was like, I want to watch this.
What is it?
I mean, it was like very she was just like, she felt like staying there.
You calling the situation off? So, I'm going to talk about he's going to but the core part is 7. It's now 50.1 to 49.9. Basically, under 20,000. So here's the question. Most liberal counties enter voted on 7. And the reason why is because the ballot is 3 columns. The first column, the first 8% that were used. And then the bottom 10% was the Senate. And the other 2 columns were just the other. So if you just look at the ballot, there are people who consistently thought that you don't have the left column is just instructions, and the second and third are all voting as they never saw the Senate. So Broward County, I saw an article somewhere saying that compared to all 6 separate counties, and how it was used to Senate or whatever, and I'm going to get over hilarious. It's so funny. For political science services, it's kind of because Ray Reagan is it is where it's like if we said the ballot, it's like how much less likely would you be to fill in that vote. So it's if it's any consolation, it was clearly a consolation.
And not
No. Broward County supervisor election. There are certain guys that be like, yeah, this is bullshit. So yeah, okay. What is that one count? If you show up, you just go around. That's good. You should go to archery.
I just kept
All the first ones.
I think
Some people say that there's a lot of 1 or 2 hours of search on taking all how they say you're an hour as soon as it's popular, it's like who never saw Walk
yesterday at 5, some people talk about
wow. Also, all that content built major respects for shouting out. All the systems. When you come to me up, yeah, I remember they didn't. You leave me for myself? What? You leave me for now? It's a great job on the scene. Not to go out the back. Like a big office, you know, common area where you have and I was like, I'd like to work in a place like this. Yeah. No 164. I mean, even better. I mean, if I go to a culture police, it's like, that's the reason it's great. It's still I saw like a video today. Let me see. I actually have questions for you. You said most of the audio. Well, who are you going to do? We all have $500. We all have all this money. Well, I use, I think, two. Think about all the video clips you can't do. You can do something. Actually, I don't That's hard to do. Why did I do this? Why did I do this? I mean, I'm going to do it. I'll call it. One of the we're not. He's a bad guy with HTML structure the page. I'm like, he's like, you can't do this legal guy. I'm like, I did because you have like 2 pumpkins and you all just like, you know. They have like some really interesting things that they do. What else fits in there? So annoying.
I was like, this is what I'm.
All right, folks, if everyone can take their seats, we're going to get started. And we got to get this to this one because my team is using Presto and they're very eager to hear this talk. All right, so next up we have Camille from sunny Boston, all the way down to talk to us about Presto. Thank you.
Hey, hello everyone. Thanks for coming. So I'll be talking about Presto, which is fast SQL engine that can run on basically any data. I'm curious who already is using Presto or heard about Presto in the audience. Okay, I see some hands. Good. All right. Okay, cool. So the short history of Presto is it's about 6 years old, open source project, first developed by Facebook for their internal usage to basically make queries fast again, right? Because after moving to big HDFS and dealing with petabytes of data, all this queries became really slow, and Hive wasn't able to interact at that time. So they built a new engine from scratch completely. So my team is actually part of the Presto community for over 3 years by now, and we contributed a bunch of features. I will talk about them later. But in a nutshell, Presto is essentially a great SQL engine. It's not a data warehouse. It doesn't own your data. You keep your data in your own favorite format, whether that's cloud storage or HDFS or any kind of storage, and you can actually see a long list of connectors that Presto ships with today that you can connect to from Presto, right? So you can issue SQL statements and refer to your data, your tables defined, either HDFS or S3 or blob storage or MySQL or Cassandra and a bunch of others, right? And this list of connectors, different data sources for Presto grows basically every month because lots of companies using this software and they're contributing connectors to the platforms that they want to query. Not only you can query individual platforms itself, you can actually drive queries that are joining tables from multiple data sources at once, right? Which makes it pretty amazing for sort of visualizing data access. Right? And then because of the SQL engine and the team is actually aiming to provide full ANSI SQL compatibility, you can actually use a bunch of BI tools and SQL development tools, notebooks, and all sorts of different tools to access Presto itself. You can still obviously write your queries by hand if you prefer put them on a command line, right? But most of your users will be more comfortable with those BI tools. So you might be curious, like, who are Presto users? There's actually a lot of them already. And the giant user is obviously Facebook because they developed this in the first place and they invest a lot in the project still and from thousands of nodes. But there's a long list of other companies. So from financial to media, telco, all over the place, big and small companies. And if you are already using Presto but you are not on this list, let me know and I will fix it. If you are not on this list and you are not yet using Presto, let me know, we can fix it too. Right? Okay, so some of the biggest users that have Presto in production are, yes, Facebook, but also Uber, Twitter, Lyft, LinkedIn, Netflix. So all the big guys are using this technology already at massive scale, right? So you can run clusters, hundreds of nodes. Each Presto scales, it's reliable, and highly concurrent SQL access. And Presto is pretty unique because you can run all cloud, on-premises, you can run in a virtualized environment, so it's very, very flexible how you want to apply it. That's why it's popular among all these different applications, right? It doesn't try to shuttle you into like one way to do things, right? So you can roll your own infrastructure if you want that. So for example, Netflix was originally using this in the cloud, using sort of standard EC2 instances. Last year, we started migrating this to a container-based environment. They're not really using Kubernetes as something they developed in-house, but it's basically sort of flexible container infrastructure, so you can scale the number of containers whenever your workload increases for a particular application. Cool. So a quick overview of Presto architecture. To enable this parallelism and scale, since running on multiple nodes, and as I mentioned, it's very flexible how you want to deploy it. But essentially, in sort of logical architecture, you have one coordinator, which is really the brain of the system, and multiple workers of actual query processing. So the coordinator will accept a SQL statement from the client, and then do a sort of standard parsing, analyzing, and planning the query execution, and then the scheduler will take care of sort of orchestrating the actual parallel execution of the query across the workers. The workers themselves, basically, they kind of read the data from the storage, and then basically apply all the processing like projections, selections, aggregation, joins, and they kind of all collaborate to compute the query. And query, obviously, in this example doesn't show that, but the query may be obviously multiple stages, lots of different operations, but at the end, there is a final result that will just return to the client. It's pretty unique in Presto versus other SQL engines is that it's actually pretty pluggable. That whole storage layer that I was showing at the bottom on the first slide is essentially a pluggable thing, which means you are not tied to any specific data source. There's actually API to develop connectors to all your storage engines. So in this picture, I'm showing 3 different pieces of that API. So there's metadata API, which allows Presto to understand what are the tables and schema and columns and data types that are exposed via your data source to Presto. So Presto will understand this, the relational mapping from your actual data source to sort of SQL standard objects. And then there is data location API that essentially allows Presto to understand how to parallelize the execution of the query, right? If your data source is just a single node MySQL database, it will be essentially like a single threaded access, right? But if you're, let's say, sharded MySQL, then that data location API, you can implement that the way that exposes the parallelism to Presto, so that multiple Presto workers can read data in parallel from your storage and achieve great speed up. And then actual workers have data stream API, which is essentially, okay, I got this data parallel unit, what do I do with it? I got the split, right? So I just need to understand how I sort of transform the stream of bytes that's coming from the data source, and how do I translate this into rows and columns that I'm actually going to process, right? And then the rest of the execution, right, engine is completely agnostic to what's your data source, right? There are no specific optimizations for this or that format. Everything is sort of contained in that connector API, right? So that's basically pretty powerful engine because pretty powerful architecture, because now we can completely replace your storage engine and move from one to the other. For example, say you have HDFS on premises, you decide to move to the cloud, right? Your users are completely unaffected, right? Like your SQL users, they see the same set of tables, the same set of schemas, right? and the queries will not change. You just sort of move the data and map them, map that data properly to tables. So that's that, and the architecture. There's obviously lots of details that I can dive into during the office hours. But I was sort of trying to motivate why people would use Presto, and it's not obvious already. Well, Presto has an advantage. It's actually a community-driven open source project. Unlike many of the SQL engines, especially from the Hadoop ecosystem, if you're coming from that environment, like each open source project was essentially driven by one of the vendors, right? So if you happen to use, say, distribution A of Hadoop, then you'll be stacked with Hive. If you're using B, maybe you have Pub, right? And maybe sometimes you get Spark SQL, but maybe it's an older version of Spark SQL that ships with that distribution. So it's pretty much you're under their influence and control, what you can use on your platform. With Presto, it's pretty amazing because of those giant users of Presto, they are driving the development in the project, and the community moves essentially based on the needs of those big users. And then if you need help, you can go to the mailing list and roll this yourself. Right? You can also ask Presto experts for help. So that's that. It's a pretty amazing open source project. Lots of different initiatives were built on top of Presto. So you might be familiar with Amazon Athena. It was basically they took Presto and they built a service on top of that, right? So it's basically I think another validation of Presto being amazing SQL engine for the cloud and those flexible deployments. Another big thing about Presto is it's high-performance SQL engine. Thanks to recent advancements of cost-based optimizer, proven scalability of up to 1,000 nodes, and high concurrency use cases that are run by these big companies. It's basically when you enter the Presto ecosystem, you can have this confidence, right, that I'm not going to hit like some bugs that were not yet exposed in terms of scale, performance, concurrency, right? Because all those big guys already found those bugs and fixed them, right? So I think that helps a lot in adoption. It speaks to the maturity of the project as well. And then a major sort of fundamental thing, which I touched upon already, is the separation of compute and storage, right? If you were entering the Hadoop ecosystem, say 8-10 years ago, basically when I started, right, into Hadoop and big data, like there was this mantra, yeah, bring compute to your storage, right? Like tie them together, right? Because shipping data is so expensive, right? And it's very costly, right? You need to bring everything into your Hadoop cluster. Everything needs to run inside, right? That's no longer true, right? All the modern architectures right now separate storage from compute, allow those two layers to scale independently, allow you to grow your data without limit, and also scale up and down your compute whenever you're ready to pay for additional compute, right? And allow you to save costs of compute when you're not using your cluster, right? Or you're running fewer queries because of the holiday season, for example, right? And the fact that Presto can access all the different data sources is also modernizing your architectures in the sense that you are not necessarily required to bring all data into one place, into this one central data warehouse that needs to go through all the ETL process, and basically before you can hit the insights, you have to wait a long time, right? So you can bring some insights earlier when the data is fresh in your data source where it's first arriving, right? So for example, you can talk to Cassandra and get some latest updates from there. You can go to Kafka and fetch latest events from Kafka, right? And combine that with the historical data. So before that data is properly transformed into the optimal long-term storage format. So that's basically it. And then I mentioned this, it's community-driven, there's no vendor lock-in. And what I mean by this is you're not tied to any vendor anymore, you're not tied to any cloud vendor, right? Because you can actually deploy Presto in any of the public clouds. You can run in your private cloud. If you that's the strategy of pursuing. You can basically do it anywhere you want. And then you are tied to a specific storage engine, right? So if, for example, S3 becomes obsolete in 10 years, right, which seems crazy right now, but let's say it happens, right? You know, there will be essentially some development in Presto to develop a new connector for the new data platform, and you will be still using Presto on top of it, which is pretty amazing to sort of separate the responsibilities. So I talked about Presto's great ANSI SQL engine, which essentially means it can basically run most of the SQL statements you can imagine. Like you can take complex workloads from, say, Redshift or whatever is your favorite MPP SQL engine today, and run them on Presto pretty much without much changes. But Presto also spans beyond ANSI SQL by offering a huge long list of various functions extensions. So some of the common use cases that we see are people using this for sort of parsing your textual data, log data using regular expression functions. There's a huge list of those available in Presto already. There are Lambda functions and expressions built into SQL, so that basically again is an extension to Presto itself and to ANSI SQL standard, but allows you to sort of have more expressive and sort of more concise expression of your SQL transformations. And also geospatial functions. Big new feature, not too many people know about this yet, but over a year ago, actually guys from Uber developed pretty neat extensions to Presto to allow geospatial analytics through SQL. And now they published this, they contributed back to the community, and now Facebook also picked this up, and they're putting lots of effort to optimize execution of those queries, especially if you're dealing sort of very large data and you're joining on geospatial conditions other than standard equi-join conditions. I'm listing some examples here on the right, so we can take a quick look how you may structure those kind of computations in Presto. Right? And it's pretty amazing that you can do complex analytics like that in your SQL using some extensions to it. And then, sort of to complement your standard ANSI SQL data types, you can also use JSON, arrays, maps, and complex structs to sort of process more of sort of semi-structured data inside Presto as well. Cool. So I mentioned up front that there's a bunch of tools that can work with Presto. Because Presto is open source, naturally some users expect various open source tools to work for as a clients, right? So some of the popular tools we see is Redash, Superset, which is actually coming from Airbnb, and Jupyter Notebook as well. So those are sort of gaining popularity now. But because Presto ships with JDBC and ODBC drivers, you can connect to virtually any tool that will be working with your standard BI and SQL environments. So if you have Tableau or things like this, they'll need to work SQL developer even, so whatever works for you. And then people are embedding Presto inside their applications, right? So there are lots of bindings like C, Go, Java, Node, Python, and so on. So you can actually call out to Presto from all those different languages using sort of the standard methods available to those languages. And then in terms of extending Presto, right? You may have a favorite GTF function or GTAF, right? It's like, okay, I want to make sure that this runs inside Presto, right? So Presto has those APIs. You can develop those functions, follow examples from the documentation, and essentially deploy a jar with those functions into Presto, and you can use that SQL. New SQL functions developed inside your SQL statements easily. And then there's the whole connectors API, which allows you to develop connectors for data sources that are not yet supported out of the box, or maybe you might be touching your internal systems that are not sort of public interfaces, and nobody is able to develop those connectors. So we see people developing connectors to their internal platforms that expose REST API, right? Because those platforms may serve data, and this data is not available through other means, they may develop a simple connector to basically reach out to those platforms and sort of represent this data from the REST calls as tables and columns, and the rest of them can run SQL on top of that. So to make things easy and to sort of tie this back to what we do, right? So we contribute a lot to Presto itself, to the core, but also we sort of try to make it more easy to use for our customers. So we can sort of have our own offering of Presto on AWS Marketplace, and it's fully integrated with Amazon services. So Amazon S3, Google Catalog. It ties into auto-scaling available in AWS, which means that you can actually start using Presto as a small cluster of 5-10 nodes, right, pay as you go, and then if your needs grow, you can sort of auto-scale this to a larger number of instances, pay for that spike, and then shrink back when you're not using Presto that heavily, whether that's 9 hours a weekend or 4 days or something like this. And then if you reach sort of a certain scale, you're really big users, some of our customers, you can sort of get an enterprise license from us and sort of have custom pricing as well. And follow the links if you want details. So we recently also entered Azure AG Insight, so you can use Presto as an application on top of Azure AG Insight, which is their Hadoop platform equivalent of EMR on AWS. And on that platform, you'll be talking to blob storage, data lake storage, Hive Metasploit that ships with AG Insight, and Power BI, and all that sort of Microsoft ecosystem. And it's also great if your company is pursuing sort of hybrid cloud or multi-cloud strategy. Presto is a great bridge, right? Because you can serve your use cases on premises, but also AWS and now Azure, right? So you can sort of use the same interface for your users across all those environments, and they don't need to learn new syntax, new language, new tools to interact with SQL and their data. Okay, so you might be curious, like, what makes Presto fast and appealing, right? So some of the internal considerations that were part of the initial design of Presto when Facebook engineers started developing this, like those 4 guys who really started working on this project in 2012, they basically took sort of the best chapters from the classic database architecture and NTP SQL engine. They took all those best chapters and best practices and developed Presto according to those sort of state-of-the-art NTP engines, right? So in many ways, what the execution of Presto is very similar to what you can find in sort of parallel database engines, and I would name things like, say, Netezza, Vertica, Greenplum, other Redshift to some extent, right? So some of those considerations on the execution are very similar, which makes Presto uniquely positioned to challenge those proprietary old-school data warehouse solutions, because it's actually following the same implementation sort of design and details. So it's NTP engine, right? But unlike things like Hive or Spark that are optimized for fault tolerance, long-running jobs, environments that can break at any time, Presto makes a trade-off of optimizing everything for performance, which means the data, intermediate data between various operators and stages is pipeline across those workers in memory, right, and over the network, right? So there's no like checkpointing, making up sort of fallback mechanism, right? Basically, pipelining intermediate results as soon as possible and try to get the answer as quickly as possible, right? And that basically means it can achieve great latency at the expense of fault tolerance, right? And that's basically because Presto was developed to be this low latency, high performance, high concurrency system, right? So you don't expect queries in Presto to run hours, and the likelihood of failure is pretty small if you're running seconds worth of execution, right? So it's easier to sort of restart the query and basically come up with the answer again, rather than to try to fall back to some partial result, because it's worth to redo it's worth to redo the old computation and arrive at that result faster than to basically do this step by step and retrace your thing. So that makes Presto complementary to some of the technologies, so Spark and Hive, because those guys are optimized for long-running jobs, data pipelines, EL, but they're not optimized for low latency, high concurrency workloads. Presto is good at. So those are the design considerations. Anyway, so to sort of dive into performance, right? Presto is optimized for columnar vectorized processing. So internally, its data is represented as columns and vectors. The moment it gets out of the storage, it's transformed into this internal representation that's very efficient. It compiles the bytecode, so it compiles your query into bytecode to sort of save your CPU cycles. It's sort of custom, memory efficient data structures internally to again make fewer runs of GC, right, and things like this, and multi-threaded, multi-core execution, so it's trying to get as much as CPU power out of your machines as possible. Optimized for the columnar format, so if you already store data in your columnar formats, such as ORC, Parquet, or Hadoop or S3, Presto will be having really optimal path from those column storage on disk to internal memory representation that's also columnar. And then recently we introduced a cost-based optimizer to Presto, which allows us to execute very complex queries, much more efficient, faster, but also use fewer resources, and basically approach those speeds of the commercial SQL engines. To just quickly recap what CPO is a whole presentation I gave at the DataEngConf Summit earlier this year, but we basically leverage statistics. The initial version, you put statistics from the Hive metastore that most of you already have, right, and store your stats there. And we leverage that to do join reordering. If you have 5 joins, we try to predict which ones we should do first to save you on memory and CPU and arrive with better performance at the end. And then we do things like decide automatically which join type we should use, so you don't have to hint Presto whether it's using your partition join or broadcast. We can make this decision automatically, and we can also pick left and right join, sided join automatically for you, again to save your CPU and memory. And we have a whole series of blog posts on the internal design and implementation of cost-based optimizer in Presto on our blog. And then just to give you sort of a teaser of the results, right? So if you compare Presto without CPO and then sort of our early release with CPO, which was released back in end of March, those are sort of some of the speedups you can achieve, right? So we take a very complex workload, define the TPCTS benchmark, which is essentially a real kind of workload with like 20 plus tables and so on. And you see the more complex queries, we actually higher speed ups because now we can predict execution and what's the optimal plan to execute those queries. And that means your queries will be faster, so your users will be happy, right? You're using fewer resources, which allows you to run more queries concurrently and reduce maybe your expenses on the actual hardware growth because you're just smarter how you execute your workload. And while you can do lots of tuning manually, like at some point, at a certain scale, it's just impossible to predict all the user queries, right? So you want CPO to solve those problems in majority of times, so that you don't have to do this manually. And actually, our friends from Facebook, when they pick up our work on CPO and they run this on their production workloads, they were very impressed because CPO was smart enough to basically never regress versus like highly tuned, manually tuned queries that they had in production, and also uncover some potential speed ups that they were not able to achieve by hand because nobody thought about this particular execution path. So it's actually proving to be very efficient even for the smart engineers at Facebook. And if you're running in the cloud, right? So what does it mean, right? Well, you can run your workload on fewer machines, right? Which means you're paying less, right, for Amazon infrastructure. So that's great. You can run this faster. You can also execute more queries within your constraints of the cluster. Say you have 10, 20 nodes. You don't want to expand your cluster infinitely. You can run more queries without failures, right? Because you are not exceeding memory allocations that are available to your cluster. And that basically means you can either run a smaller cluster, pay less, or do more work, more queries at the same cluster, right, at the same cost, right? So that's pretty amazing. And so when we run the same workload on the Amazon infrastructure, over 60% of queries, almost 2/3 actually, are 5 times X or faster, right, than the baseline Presto from EMR that you can get from Amazon, right? So it's pretty amazing, and we haven't seen any regressions to it. So very good results. Full detailed disclosure of this benchmark is under this URL if you're curious. And then, you don't have to take our word for this, obviously. We contributed a lot to this effort, right? But there are independent studies right now on the web from Fivetran, Concurrency Labs, and a few other users of Presto. And they basically compare Presto versus Spark, Presto versus Redshift, Presto versus Snowflake, BigQuery, all these other technologies. And you can see how Presto fares against those, right? And not to spoil the surprise, but it basically Presto sort of is in the same ballpark in terms of performance and very, very good cost benefit as well. So you may want to check this out if you're really unhappy with your builds on other SQL engines. Okay, cool. So just finish off, right? Like, if you are not using Presto and you want help from us, we are sort of one company that sort of helps to get you more out of Presto. So we are sort of about a year old, but we actually were part of Presto community for over 3 years, and we're contributing a lot to this open source project. So you can see contributions from our team on GitHub. We have our own distribution of Presto for on-premises and cloud environments, which is basically pre-packaged, easy to use, stable, tested. You can kind of think of us as, like Cloudera was for Hadoop, right? Or was for Hadoop. Like we kind of provide that kind of level of service to the community. And we support customers in production 24/7, right? So if you want to roll this in production and you don't want to own it all the time, and you want someone to call and fix your bug or triage the performance issues you see, right? Like we can help with those things. And we have some subscription add-ons for enterprise users too. If you're curious, I can discuss the details and check us out at the table as well. And some of those major things that we contributed to the open source to everyone's benefit is extensions to ANSI SQL to make it fully compliant, various performance improvements to execution, security integrations as well, like Kerberos LDAP integrations, spill to disk, right? So if you're running out of memory on your cluster, you might want to sort of have ability to spill to disk locally rather than fail it through, right? So that's another thing we completed. And then Cosmos Optimizer was basically a major effort that my team was pursuing for over a year, and we sort of shipped that in March and contributed back to the community as well. Okay, cool. So that's all. We have a table outside if you want to grab a t-shirt or a handy, and things like this, stickers. You can follow news on Presto, on Twitter, blog, and newsletter. And obviously I'm hosting office hours as well if you want to dive into details. Really run Presto, you have some challenges, you like to share your experiences. Always happy to help any community members and learn more about Presto users. Thank you so much.
We have a few minutes for questions. Anyone have anything they want to ask?
So can you use Presto for like unstructured data, and can you use it for like against NoSQL data stores? That's one. And how does Presto compare to something like Dremio?
Yeah, great question. So we scroll back here. So some of the I guess NoSQL engines that we support today would be Redis, Akimolo, Cassandra, Kafka, MongoDB. Those are currently supported. We are hearing about HBase a little bit, although less than in the past. But that's another connector that might be supported at one day. Yeah.
Do you need to predefine the schema?
So some of those engines expose SQL-like schemas. So for instance, Cassandra, you can query, and they will give you a list of tables and list of columns and things like this. So some of those do. Some of them, like say Mongo, you have to. I think you have to apply some mapping, and I think that also applies to Kafka. You have to provide some mapping in your configuration. So your connector is like this glue that's between your data source and Presto. So that connector code typically comes with some configuration, and you can plug in different things there to allow us to understand better how to map this. So the inherent data source schema to sort of more like database schema that Presto can understand. Yeah. So it depends on the connector exactly. It's all documented online if you'd like to check this out. But yeah. The second question about Dremio. Dremio is one of those examples of SQL Hadoop that was developed by a vendor called MapR, if I recall correctly, right? It's shipping with MapR distribution of Presto. It's a Apache project, right? It's SQL. I guess when people ask me to compare this, like, I think Dremio has this very neat angle of like discovering your schema at runtime. Right? So you don't even have to define it, which is a pretty amazing feature. Other than that, I'm personally not aware of like big community users of Dremio that will show me numbers like those, which I think their adoptions will be limited to the MapR user base, and that's why they're not really publicly speaking about this.
I have a question about how you see customers use Presto. At least when I first became acquainted with it, it seemed like more of an OLAP query engine, but it certainly makes it easy to run batch-style ETL because of the connectors. It's kind of a debate we always have internally, and I'm curious what you see more people out there using it for.
Right, so I mentioned earlier in my talk that Presto, by design, is optimized for those shorter, faster queries of concurrency, right? So that was true originally, and it's still true because Presto doesn't have fault tolerance built in, right? However, when you talk to some of those Presto users, some of them use Presto for both ETL and so low latency BI kind of workloads. Even internally at Facebook, they migrated off a bunch of pipelines from Hive, which was obviously fault tolerant but super slow at scale, right? So they migrated to Presto. They did some sort of engineering to break those long queries into a series of smaller queries, so that they can actually like manually checkpoint write the intermediate output to like disk HDFS, for example, right? And that way they can enable some replay logic. But because of the benefits of Presto speed, they can actually basically save 80% of the cost of running that pipeline, which is a good trade-off regardless. So you do see people playing with this idea and doing this. It's still not like a common practice. Common practice is still use Spark or Hive, but I think it's getting some popularity. And if you do it sort of in a pretty little smart way, you can help with that as well. Nice.
One thing that Presto promises is, its ability to do federated queries, right? It's Presto connects with multiple databases. So, let's say I have two or three databases like MySQL, Oracle, and Teradata as well, right? I can connect it to all of them, and I have a query that needs to, get data from all these three data sources. Can this be done in a single query? how often do you see that in real world? This kind of multi database based requirements.
Yes. So definitely Presto can be used to federate queries or virtualized data access. So because in your Presto system, right, you can actually define multiple catalogs and mount Presto, like a Presto cluster, and then you say, okay, this is my HDFS cluster, this is how you access this. This is my S3 compatible object store, this is my Cassandra, and you can actually run queries across that. Which means you can refer to tables from different data sources that are mounted to the same Presto cluster. I think maybe I skipped that detail, right? But Presto will actually push down processing to the underlying data source for things like predicates and column selection. So it will only fetch the actual data that it needs for the particular query, rather than bring entire data into Presto, right? So it's very efficient, and yes, you can run queries that are correlating data between different systems. That's a pretty common use case too.
Any last questions? Going back here.
Hi, so my company's been using Amazon's Athena, which you mentioned before, sort of a managed version of Presto. Honestly, sometimes banging our heads on the wall with it because it seems to be claiming to be serverless, but actually having limits, looking much more like a traditional server. So can you contrast sort of like your approach here is you do have sort of provision capacity ahead of time. How do you compare your approach and overall performance with Athena? I see a lot of comparisons you have on your blog with Presto on EMR, but not necessarily with Athena.
Yep. Yeah, great question. So I would say yes. So Athena was built using Presto code, right? It's exposing Presto or query interface, and they basically picked a different business model, right? They charge you per query, right? Not per cluster running Presto like normally on EC2, but per query, and they look at how much data you read, and that's the basis for billing you, right? Honestly, yeah, it's obviously you can compete between these two approaches, right? Running the fixed cluster or scale cluster that you pay for compute, or we charge per query. What we see, I think, that to be really popular for is infrequent queries that are unpredictable. Because once in a while, want to run a big query, you don't want to spin up a cluster, manage the whole infrastructure, right? Yes, it has those limits, and we heard that feedback from our customers too. Some codes fail, and so on. You cannot actually expand capacity to black box, the SQL interface, that's it, right? So it has those challenges. In terms of performance, right? So you have to guess like what's behind Athena, right? Like some people say it's 10 nodes, 20 nodes, whatever, right? So yes, there will be limits to how big queries you can run on Athena. No limits if you provision your own Presto cluster, right? Because you can scale it to 100 nodes, whatever, right? So no limits there. If you're running persistent workload, lots of queries concurrently, you probably want to own the infrastructure because you're not building per query, right? You just build fixed amount or more or less fixed amount for your compute time, right? So for real production use cases, definitely recommend getting your own cluster. You can also tune it for your workload, which you cannot tune Athena because again it's a black box, right? So those will be the considerations. But, yeah. Thank you.
All right, thanks everybody. Office hours upstairs, room 302. Otherwise, hang out here. I think we're hearing about reactive Kafka, which I'm kind of excited
You gonna go? I want to ask you too. So I was going to ask
Important, yeah. And they were like, oh, what people you should do.
you know what we do.
And I'm like, oh, fault tolerance. I think like,
No, the fault
tolerance is when like nodes go down.
No, not just that, but also when the nodes go down, but which is you start the job, you measure that's kind of as opposed to starting from scratch. Right? So you like you guys keep pointing. So the pointing is just actually Something that's no, it's just for me. It's make the space. It doesn't seem like I'm talking about the software-based optimization. The software-based optimization looks to have like sort of lazy. Like the execution plan, right? How can you say, hey, you got this execution plan with 10 steps? I can actually make it 7 because of the software-based optimization. That's the laziness. Yeah, that's the laziness. I do want to go outside that. So it's a bit like this people that are not so traditional Spark SQL scripting. Original Spark, right? High. The high is ready. Like, what are you trying to do? When you load the tables, it's scratched from wherever you have them, like an S3 or something database, right? At the end of the day, Spark is already sleeping. There's no good luck changing you know, you have the Spark concept. They don't have much to we can do it, but I just like more than using the system. You know what I think a good like research project could be? Do that on the set up a small like so basically just do a little Amazon tuna like sort of test and do a comparison like an edge builder and you're doing it you could try it's going terrible but once you figure out how to put it in their side doesn't have a lot of all it has is spar learning it doesn't have a Presto. Well, we gotta play with it. He's comparing there. Right. I thought he was like,
all right, folks.
Yeah, let me.
Everyone take a seat. We're going to start, and we're getting crazy as we get later on in the afternoon, and Sean's going to actually walk around, which is actually how I like to talk. I'm Italian, I do this. All right, next up we have Sean Glover from Lightbend. We'll talk about Alpaca Kafka, which honestly is really near and dear to my heart. I've been doing nothing but Kafka for the last few years, and I have not used Reactive. So I'm kind of psyched to hear about it. So thank you.
Do you want to go?
All right, thank you. And Active Streams, and we're going to dive into a specific implementation in Alpaca Kafka. Since I have limited time, I chose transactions for transactional workflows with Kafka, so I figured that might be interesting. So my name is Sean Glover. I'm a principal engineer at Lightbend. I'm a member of the Fastio platform team, and Fastio platform is a commercial product that Lightbend provides. It's sort of like Cloudera or Hortonworks. It's a distribution of stream processors, as well as support for underlying infrastructure. We started with DC West and Apache Mesos, but we've recently moved to Kubernetes and OpenShift. And we support Kafka under for all of these stream processors as well, and that's what I specialize in on the team. So because of that, I contributed to the Kafka ecosystem, including Kafka itself. I helped develop the Scala DSL for Kafka streams. I worked on Alpaca Kafka itself. It used to be called Reactive Kafka. It's been around for maybe 5 years, so you might have heard of it by that name. Streamzy is a really neat project. I encourage people to check out if they want to run Kafka on Kubernetes. It's pretty mature. They just released their first production-ready version. And if you use Kubernetes, you'll definitely find that project interesting. And then the DCOS Commons SDK is a library to help write stateful services to run on DCOS and Apache Mesos. So I was involved in that last year. So Alpaca. Alpaca is a open source initiative to integrate disparate systems together. So it's a container project that it's basically a container project around all these different connectors to various systems. It doesn't have any source code itself. It just has documentation. It might have source code in the future. But it's a very developer-centric set of modules to use to connect these systems together using ACA streams. And we're going to talk about what ACA streams is and why you should care about it. But it is very similar to other projects out there used for ETL operations like Apache Camel, Kafka Connect. Unlike Connect, it's not declarative. They're just modules or libraries you bring in, just like any other library dependency. And it helps people build these reactive integration pipelines using a principle known as back pressure, which is one of the key attributes of ACA streams. And you can write these apps in Java and Scala. So here's a kind of logo cloud of the different connectors that are available. I put them into groups. There's connectors for cloud services, so AWS S3, S2S, DynamoDB, PubSub for Google Cloud, data stores, pretty much all the big ones you can think of, like Cassandra, HDFS, Mongo, Solr. And then, of course, messaging. We support implementations, AMQP implementations like RabbitMQ, JMS, and of course, Kafka itself. So the Alpaca Kafka connector is the connector to connect Kafka to ACA streams. And it was formerly known as ACA Streams Kafka, and before that, Reactive Kafka. It actually predates the Alpaca initiative, which started a couple of years ago. It was created by a company called Software Mill about 5 years ago, I think, and eventually brought in as an official ACA project. So I work for LightBend, which stewards the ACA project. So they brought it into the under the ACA GitHub organization, and as a result, a lot of the ACA committers made it a lot better. It's used by a lot of our clients, our commercial clients, but it's probably one of the most popular, if not the most popular, client library for people who are in the Scala ecosystem, developing Scala apps to connect to Kafka. And it's used in some of our other open source projects too. So Lagom is a microservice framework. It's used as one of the options for message passing between microservices. And it's used in a new commercial product we're shipping early next year called Fast Data Pipelines as the basically the glue between the components in your pipelines. Because it's been around for so long, it's the top downloaded module for Alpaca Kafka. These are just stats for August 2018. I don't have updated ones. So ACA Streams, let's talk about what makes ACA Streams unique. So it's a toolkit to provide low latency, complex event processing, streaming semantics using something called the reactive streams specification. And it's implemented internally using ACA actors. So like the old actors, actor systems you might have heard of. ACA is a JVM-based implementation of allowing you to build actor systems. It was originally created to simplify streaming semantics within actor systems. So if you're familiar with those, you'll know that there are the most basic parts of them are ACA actors, and then they communicate with one another asynchronously by passing messages back and forth. So you can that's a pretty low-level communication model, and you can do any kind of streaming semantics you want with that, but it's fairly difficult to model more kind of high-level abstract semantics. So actor streams was the reason it was created was to make those streaming semantics easier in various parts of ACA for the types of systems that you're building. So it reduces a lot of boilerplate and makes it easier to build these types of systems with less experience. It's built in an actor system itself, but it's that's not exposed to the end user. End user can pick up this library, bring it into any JVM project, Java project, and start using it. They don't have to know what ACA actors are. But we'll talk a bit more about ACA actors and how ACA streams is designed in the next slide here. So the most basic ACA stream is a source and a sink. A source has at least one outlet, a sink has at least one inlet. And then you have this arbitrary number of flows in between. It's doing some sort of processing on your data. And the big difference between ACA streams and other stream processors like Spark or Flink or Kafka streams is that they support this back pressure protocol here. And so there's two communication channels. There's two flows happening within an ACA stream. There's obviously the user-defined messages are flowing downstream, but there's also an upstream channel that's used for this back pressure protocol. And we'll explore a bit more about why you want back pressure, but in a nutshell, it's basically to accommodate the fast producer, slow consumer problem, where you don't want a fast producer overwhelming any of your systems downstream. So this allows you to signal upstream, hey, can you please slow down so you don't overwhelm me and make me crash, because a lot of systems don't have, well, whatever the weakest point in your system, your internal infrastructure might be, is probably the first one to fail, and oftentimes there might not be a backup, and you'll get some cascading failure across your infrastructure. So back pressure is really good to, is a really good way to handle scale like that if it works for your requirements. So the reactive stream specification is an initiative to provide asynchronous stream processing with non-blocking back pressure. So ACA streams is basically an implementation of this. It borrows a lot of the same principles from the Reactive Manifesto, which is a set of principles to build, to help build flexible, loosely coupled, scalable systems that communicate with asynchronous messaging. So this spec was spearheaded by Lightbend, but it has a lot of contributions from big companies in the streaming space like Netflix and Red Hat, and Pivotal, and others as well. So like I said, ACA streams is one implementation. There's several JVM implementations out there. These are just a few. There's implementations on other language runtimes too. It's not specific to the JVM. And it was also proposed to be included in the JDK, and it was accepted not too long ago. So as of JDK 9, there is a set of types under this package that is semantically equivalent, one-to-one semantically equivalent with all of the terms defined in the reactive spec. So what we're going to see is over time, once the community moves past Java 8, we'll probably see most people picking up JDK 11. Once most of the community has moved there, a lot of these libraries are going to start having releases that use this implementation instead of their own internal implementations. So this is a little demo on how back pressure works. So each source, flow, or sink here is represented by an actor behind the scenes. And there's several important traits of an actor. One is that each actor has this little mailbox. In this mailbox, is basically where the messages kind of buffer before they actually enter an actor to be processed. Each one of these components, they're called graph stages. I'll start using that term from now on. Each one of these graph stages, like an actor, only processes one message at a time. And that's what makes it easy in actor systems to model concurrency. You don't have to worry about another thread closing over the same state that your path of execution might be currently on. Actors give you that isolation, and if you want to model concurrency, you just have more actors, and they all have their own mailboxes, and then they can concurrently do things. But by having them by processing one message at a time, you get a lot of flexibility in defining state, and that's the third thing. Each one of these graph stages can encapsulate state within them. Okay, so to begin the demo, when you start your active stream, there's nothing happening, there's no messages flowing until the sync realizes that it has no messages to process, and there's no downstream graph stages, it's the end of the line. So it sends a demand request upstream. So this uses that back pressure channel I showed on an earlier slide. It sends this demand request upstream, it propagates to the flow. The flow doesn't have any messages to give it, so it moves up to the source. And then the source does what the source does and loads messages. And in this case, it's loading from a Kafka topic, but you could use another Alpaca connector here and load it from whatever. Once the source has some messages available, it knows that the flow is waiting for messages, so it sends messages to the flow. And then the flow is processing messages, and it satisfies the demand request from the sync and sends messages to it. So the way to get into a little more detail on how this works, you can imagine if, so a lot of people call this kind of process of streaming a pull model, where downstream things are pulling messages upstream, and it can be inherently slow in a naive implementation. So if you can imagine one demand request per message, then obviously with millions of messages, you're going to get a lot of chatter on that communication channel. So the way around that is to request more than one message. So how do we figure out how many messages we can accommodate? So that's where these mailboxes come into play. So in a normal actor system, you have mailboxes, and if you don't specify a different one, it's the default one is unbounded. So it can grow infinitely large. And you can imagine in certain scenarios that it can grow so large that it would basically run out of memory. So by default, in active streams, the mailboxes for each graph stage are bounded. So it knows exactly how many messages it can buffer, and that's what it sends when it sends this demand request. It says, I can handle exactly this many messages in my mailbox. In practice, you probably have a lot more than that. And it sends that along with the demand request upstream, and it's basically the pull side of this dynamic push-pull that we're going over right now. And then the source can then push messages downstream. So it doesn't need to wait for one demand per message. It knows it can send it back, which is basically what push semantics are doing. They're just back sending things as fast as possible. And if there's no back pressure, then you can get into trouble with that model. But because it knows it can handle up to 5 messages, that's what it sends. So this is the example of a fast producer, slow consumer problem where, and this is how we handle it in active streams. So once this mailbox is full, there's no more demand requests coming from the flow. So this situation should never happen. The message should be sent, But if it did, it would be dropped because it can't be accommodated in this mailbox. So Kafka, show of hands, who kind of knows what Kafka is? Okay, good. You don't have to talk about it much. So there's the quote, big distributed streaming system, fast, high volume, fault tolerant, all those great things. It's a relatively simple architecture, and it offloads a lot of complexity to clients. So Alpaca Kafka connector is an example of one of those clients modeling some more complex behavior over top of Kafka for interesting message delivery semantics. Kafka is really good at absorbing high load. So it's sort of counter to what Akka Streams is all about. Akka Streams is about accommodating just enough data that you can tune the mailboxes and whatever it's to accommodate more messages. You can scale them out horizontally and accommodate more load that way. But Kafka doesn't have any means of back pressure. It's designed to accommodate as much load as possible. It's like the shock absorber for your internal infrastructure. You can put it on the periphery, except like high bursts, spikes of traffic, and then your consumers can catch up at their own speed. But Akka Streams, when it loads data from Kafka, can't propagate back pressure messages over through Kafka unless you model that. But I would argue that doesn't make sense because that's not what Kafka's strong suit is anyway. So usually an Alpaca Kafka pipeline or a pipeline using Akka Streams is starting with Kafka, and then there are other components that you're communicating with over through different means. So not through Kafka topics, but maybe through just a TCP socket or a gRPC connection. And those means of communicating, we can support back pressure through. So back pressure isn't just exhibited through a single application you have running on one node. It can span multiple network hops as long as those network hops support some means of back pressure. So I already gave a few examples, gRPC and just plain old TCP sockets. So when would you use Alpaca Kafka over Kafka Streams? So they're very similar. They're both just libraries. So unlike Spark or Flink, which are frameworks and require a cluster resource manager in place to do any large workloads. Alpaca Kafka and Kafka Streams are just library dependencies. You bring it into a JVM app, and then it's up to you to figure out how to deploy that, scale it if you need to. But obviously back pressure is one unique feature that a lot of these other stream processors don't have. So if that's interesting to you, then this is probably a good technology to consider. Complex event processing. So in most cases, if you want to do any kind of CEP, you're calling out to other systems, which can be a very brittle activity. But with Akka Streams, as you might imagine, it has very good integration with Akka actor systems. And actor systems are a great way to model very complex business requirements. You can have actor systems that are a single JVM, maybe they're running in the same JVM as the stream itself, or you can have cluster implementations that span as many nodes as you want. The Akka team once spun up a 3,400 node Akka cluster. I think the cluster formed after about 5 minutes. It's an amazingly powerful way to model complex systems if you have that need. So basically, if you want to do any kind of CEP and you already modeled, all the rules that all the type of derivative functions you want to happen to this message as it gets processed through a complex CEP loop, then you can easily link to those actor systems using actor streams by just using what's called the ASK pattern. And I probably won't have time to get into that today, but I encourage you to check it out. And then complex graphs. So Spark, Flink, Kafka streams, as far as I know, they only support acyclic graphs. Kafka streams actually allows you to implement cycles within your graph if you have that need. Not many people have that need, but it's definitely pretty interesting. If you do have that need, then you can model it very easily without having to basically model it at a higher level through different Kafka topics and things like that. So what I mean by a cycle is just a loop within your pipeline. So instead of just kind of a linear downstream pipeline, you can have maybe a downstream flow sending messages to an upstream flow for whatever reason to influence that information somehow that's flowing through it. So here's some code, not very interesting. This is just the ceremony to get the clients up and running. So if you work with Kafka, this should kind of look familiar. This is Scala code, by the way. And yeah, so you can use typesafe config and have your default client or consumer or producer config in there, and then some other Alpaca Kafka config. You set all the settings this way. And then here's a more interesting example of an actual kind of end-to-end workflow of a very simple Kafka stream. And these are, so this committable source and committable sync here are components of the Alpaca Kafka connector. So this is basically what you're referencing. And you're passing in your connection details, your topic subscription. And this particular source is basically helping you model at least one semantics by including offset information for messages that you're consuming downstream so that they can eventually be committed automatically on your behalf. So you don't have to do it for you. So you don't have to do it yourself, rather. So all your business logic would be in some form of transformations here, like a map and lots of other transformations that are available with active streams. And then like I said, once the acknowledgement comes back that this thing has been committed to or produced to a topic, then it will automatically commit, every single message or a batch, depending on how you want to model those semantics. So normally in this presentation, I jump into consumer groups and talk about managing at least one semantics in more detail, but I didn't have a lot of time, so I chose one particular feature of transactional, Alpaca Kafka, and that I thought you guys might find interesting. So Apache Kafka supports transactions as of 0.11. That came out June 28th last year. So transactions enable atomic rights to multiple Kafka topics and petitions. All of the messages included in transaction will successfully be written or none will be. So that should sound pretty familiar. It's very similar to just any old transaction with a database. These semantics weren't possible before 0.11 because a lot of features had to be added to the brokers and to the clients to make it work. So before then, these types of semantics weren't possible. You could try and model them on top of Kafka, but there were certain corner cases that weren't supported where you'll always get, there's always a possibility that messages could be out of order. I won't get into the details about that, but basically it's related to how retries work within Kafka. So this solves that. So before we get into the guts of transactions, Kafka talks about 3 message delivery semantics they support. So the most ones is the most performant one. Basically, we're sending messages, expire and forget. A good example is a game client and server where you don't care about every message being delivered. You only care about the latest message. So it's using the UDP protocol, and which has it doesn't have all this acknowledgement stuff built into it, and using at most once message semantics are basically the same thing modeled with Kafka. You're just sending it and not waiting for acknowledgements before you send the next one. At least once is what most people want to use, and it's basically sending a message, waiting for an acknowledgement. If the acknowledgement doesn't come back, then we retry sending that message. So there's a possibility that we can send that message more than once, and downstream we need to either just accept that back or handle deduplication in some way. So that can be a pain. And exactly once is the holy grail of kind of message delivery semantics. And I have it in quotes here because exactly once message delivery, if you want to get really technical, is not possible. So how does Kafka claim that they have exactly once? So let me explain that a little more. So there's a famous problem known as the two generals / Byzantine generals problem that says exactly once message delivery is impossible between two parties where failures of communication are possible. So that seems fairly definitive, but what we're actually doing with Kafka isn't violating this rule, because we're doing some other things at a higher level. So in an IT networking class, you might be learning about TCP. You learn about things like at most once with regards to like UDP protocol, and at least once with regards to TCP. And then they might talk about this, how at that low level you can't guarantee that the message is only received once, processed once, sent once, and lives once in the destination. You just can't make that guarantee at a very low level. You need a higher level of abstraction and a more application kind of specific point of view to make that kind of thing a reality. So that's the key, basically. So exactly once message delivery at a low level is impossible, but exactly once processing at a higher level using a bunch of tricks or faking a lot of the things to make exactly once delivery look like it's possible is possible. So some of the things we're faking are retries until we get an acknowledgement from the sink. So that's very similar to at least once semantics. So we'll retry if a message isn't acknowledgement isn't sent back to the client. We have idempotent data sources. So when the message ends up in its destination, we have some sort of way of determining that that message has already been sent. So some kind of deduplication is happening. And the last thing is we can guarantee that messages are not processed more than once through a couple of features that I'm going to show you in a second. So here's the basic breakdown of transactions within Kafka. So you have 5 things we're going to go over here quickly. So the transaction coordinator is basically a sub-process that runs in one of the brokers, and it's communicating with a client, and there's one of these coordinators per transactional workflow. It has an internal Kafka topic known as the transaction log, and this is where all the metadata about the transactions happen, stored. You have control messages, which we'll talk about a bit more in a second. But these are basically caps at the end of the topics that you're producing to signal downstream that, hey, anything before these control messages was successfully processed. You have a transactional ID. So this is similar to a consumer group ID, if you're familiar with consumer group. It basically differentiates this program from another transactional program, and also fends off any duplicates of that program that might try and trample over the messages that you're processing. So if you have, for example, 2 programs running with the same ID, Kafka will guarantee that only one node can actually commit a transaction at a time. So they can't both commit transactions at the same time. Then obviously you lose a lot of the guarantees that exactly once is trying to give you. And the way that works is by there's a generation, a version number for every session of a transaction that's appended to the transactional ID. It's just called the epoch number. It's just an increasing number. It gets appended. So if another transactional application tries to join, it's going to, they call it fencing off. It's going to fence off the older generation of that program and say, roll back your transaction. A new player has entered the game, and your any data you have in your transaction that's not committed is null and void. And then the new application will resume from the latest committed offsets that were it will consume from the last committed offsets. So the three features that enable transaction in Kafka are idempotent producers, multiple partition atomic writes, and consumer read isolation level. So idempotent producers are really easy to explain. This is all the transaction semantics on the client, from the client perspective, are built into the Kafka producer API. So you have a client here, it's join the cluster, it has a producer ID. This is a ID that gets generated by your Kafka cluster for you. It's kind of like a session identifier. And then you have this sequence number that's 1-to-1 for every partition that you're producing to. So for each partition, you have a sequence number. So you're sending your first message here, you're starting from 0, this producer ID. The broker receives it and persists it into a partition, along with that metadata. And now the broker is expecting the next message, which would have a sequence of 1 for this particular partition. But what if something happens where the broker is trying to acknowledge that this message was persistent and that doesn't go through? The client's going to retry, and it's going to send the exact same information again. But instead of failing, the broker can simply say, oh, that's okay, it's still a successful request that you made, but you can stop worrying about trying to resend that message. I already have it. So it signals that there's a duplicate already. If it sent a sequence number, if there was like a gap in the sequence number, like it tried to send 2 before it received 1, that would be a fatal exception for the transaction. Everything would be rolled back. So this is the idempotent producer. And multiple partition atomic writes are required to make sure that the commit process guarantees that all the information, all the messages that are in the transaction, all the messages that we consume from our source topic have been read. Make sure all these things happen kind of in one operation. So this is basically it's a two-phase commit. So the first activity that happens when you commit a transaction is that it will update the transaction log with a message saying we're preparing to commit the transaction. And then once that's been acknowledged that is in the transaction log, then we can add these control messages to all the topics we're producing to, and we can also commit that all the messages we consumed have been read, and we do this all at once in an all or nothing operation. If any one of these things fails, then obviously the whole transaction isn't valid anymore, so it needs to be rolled back. Once they all happen successfully, then the transaction is committed and everything is good to go. And finally, the read isolation level is for downstream consumers of your transactional workflow. So we've described a simple consume, transform, produce, consuming from Kafka, producing to Kafka. I forgot to mention that before. It has to be the same Kafka cluster, and it has to be consuming from Kafka and producing back to Kafka. to get these guarantees. So assuming that the transaction was successfully committed, then maybe you have another transactional program downstream that's really consuming one of the partitions you were producing to, right? It looks for, if it has this setting of isolation read committed, then it knows to wait for this control message to show up before it starts consuming messages. Because it only wants to consume messages that were part of a successful transaction. So the opposite setting for this, if it's not defined, is read uncommitted, and that's basically the old, standard way of consuming from Kafka, which is basically as fast as possible, depending on some other client consistency guarantees you can tune in client config. But yeah, that's how that works. So transactional workflows are actually very fast, and in the design papers that Kafka created when they implemented some of these semantics, they did a comparison where they picked a good interval to commit transactions, like at a certain level of batching of messages in a transaction. The overhead of a transaction was negligible over time. The performance penalty that you do pay, though, is end-to-end latency within your overall pipeline. So if each one of these is a transactional application, they'll commit based on some sort of interval, whether it's based on time or number of messages. Usually it's time. And say it is time, then the latency you're going to see at the end of this pipeline is going to be an aggregate of all the latency of these transactional commits. So it has to commit a whole batch before the next one can consume them. So this is what you got to watch out for when using this in a longer pipeline. So here's how Alpaca Kafka implements this. It's very similar to the way Kafka Streams does it itself. There's basically a loop happening right here, where the every 100 milliseconds by default, which is the same as Kafka Streams, it will try to commit all of these messages. So what it does, as messages enter the transactional sink, or this can be modeled as a flow as well, the messages are added to the transaction, produced, and then we have a little bucket here waiting for the acknowledgements for every message for consuming. And then when it comes time to commit, once this interval elapses, we commit the transaction. And we have to do a couple things in order to make sure that works properly. And I'm going to go through a short workflow here of how that works. So the graph stage, this is an example of the transactional graph stage. It has a transactional status. It has a back pressure status. Is it exhibiting back pressure? Is it not? And it has this commit loop, which is basically signaling when the transaction should be committed. And then it has a transaction with the actual messages and that bucket I mentioned earlier. So this is the transaction in progress. The transactions are been begun in the last slide. It's open now. It's receiving messages. They're coming into the mailbox. They're being committed to Kafka. And these are some of the outstanding ones we're waiting for responses to. And then this commit loop elapses. And the way that we signal to this transactional graph stage, like when to stop receiving more messages, is by sending another message to ourselves. This is kind of a neat way of modeling concurrency within one actor, instead of actually closing over some code and mutating state, which creates all those kind of race conditions and hard concurrency problems you're probably familiar with. We simply send an internal message to our mailbox saying, this is the message that will actually start the transaction. Any messages after this transaction will not be after this message will not be part of the transaction. In fact, this message itself, when it's processed by this stage, actually suspends the back pressure, so no more messages can actually enter the mailbox. So at this stage, we're Okay, we're draining the messages. We waited for all the acknowledgements, they come back, and we commit the transaction using that two-phase commit. And then we get a new transaction. So here's the code. It's very similar to what I showed before. It's just the source, transformation, and commit. So yes, that was very complicated, what I just described, all the transactional implementations, but for the end user, the good news is it's really simple and easy to use. The only difference here really is that we have a transaction ID and we're using different source and sinks. So I don't have time to go into all of this, but this is Alpaca Capture was just released 1.0 milestone 1 on November 6th, a couple of days ago. It has a new team at Lightbend that's kind of rebooted it. It's got a lot of community interest now. There's a lot of new features in it. So I hope that you guys might find it of interest. So Alpaca is basically a toolkit. It's not a framework. You pick and choose what you want to use and build your own streaming platforms or microservices or whatever you want with it. And Alpaca Capture is just one component of that. So hopefully I've given you some ideas on what you can build and yeah, thanks so much.
Do we have any quick questions? Maybe we can, otherwise I'm supposed to pop up the directions to the party. If anyone has any questions, just grab John before he leaves. Here's the community party slide. Hopefully soon. We'll be rocking. Harlem County. Just a few blocks away. Hope to see some of you there. Thanks. And I'll see you all tomorrow.
I want to have a couple. Yeah. I mean, there are a bunch of people. I don't know why. Well, not this.
It is tiring. Like, listen, it seems so dumb that it's so tiring.
Yeah. Also, you kind of. That's why the notes are. I got good stuff on that. Why don't we use this one? This one? Yeah, about halfway through, I just pulled up my own like. Smash the keyboard. Something happens. Yeah, well, I doubt it's going to get warm. I told you, I feel like literally everything's short. Like things are fading pretty hard. Push that there. Are those high quality? They're pretty good. I think the low quality ones are well, they're just annoying that one. Well, I mean, they're good against that. Diamond. I was worried they were going to actually play him off and use the light and stuff.
I don't think the light. That's sort of like I'm gonna go to the you want to meet out? I'm gonna go see you. Are you going?
Almost over the jacket. I think it's Greg. This jacket? Greg. That's Greg. I think he did. Yeah, I'll stop.